And my
Yeah.
voice is also loud and clear.
Yes, it is clear.
Okay, so let's wait for 2 minutes, then maybe more participant will join. Then we will start the session. So today's session is revision session. I am Subham, and the revision session is on week 7 and 8. So let's wait some few or 1 minute. Okay, so let's start the session. Let me share my screen first. So today's session is on week 7 and 8. So I have created some slides in which I have taken some topic on only on equivalence and similarity, and rest all I have taken some question which we will discuss those, along with we will discuss concept which in which you have doubt, and you can ask regarding concept or any particular question on week 7 and 8, anything. So hope, am I audible, right?
Yes, sir.
Yes, sir, you are audible.
Okay. So let me start with the one simple a definition, that equivalence of two matrices. So the simple difference between, we can say, equivalence and similarity. Similarity of two matrices, if B is similar to A, saying to be like similarity in the set form, you will say similarity is a subset of equivalence. Equivalent. So like equivalence is defining on m cross n dimension, but similarity is needed to be a squared matrices. And when we will say two matrices, let's say A and B are equivalent if this property should hold. B equal to Q dot, or Q multiplied with, as a multiplication is as matrix multiplication A and P, where Q is a square matrix of order M, and P is an invertible also, and P is a square matrix of order N, which is also an invertible matrix. If when two matrices are equivalent, then this property will hold in both sides. That means saying if A and B are equivalent, then rank of A equal to rank of B, and if two matrices have the same rank, then they are equivalent also. Okay, so yeah, I will upload this PDF. I have seen a question on chat, so I will upload in last. I will upload this slide and you will get in your portal. And now the next is similarity. Similarity saying to be A is similar to B. A is similar to B if there exists an invertible matrix where both A and B are square matrix of order n. So A is saying to be similar to B or B is similar to A if there exists an invertible matrix writing to be like this. B can be written as P inverse time A time P. And the property of the similarity matrix is very similar to equivalent. The rank will be same of both matrices. The rank will be same. So one thing is note to be here. If A and B are similar, then rank of this implies that similarity rank of A equal to rank of B. This will not go to like this. Like if rank of A equal to rank of B, then they may not be similar. But this is not the case in equivalent. If in equivalence case, if two matrices have the same rank, then they are equivalent, but not in similarity. And the next one is the both have same determinant. So similarity have the same rank, both matrices have the same rank, and determinant of both matrices should be equal. And another property is trace of a matrix. Hope you know that. Just adding to the entries, whatever in diagonal, on diagonal, if you add this, that is a trace of matrix. And in such case, if A and B are similar, then trace will be equal. So on this basis, I have a question, which is I have taken from activity also. So let's discuss this question. So I am giving some few minutes. Many of you know the answer directly, but who like I am leaving to you to solve this. And if you know the answer, please explain the reason why this option is going to be true. And then we will discuss discussing the question, we will discuss more concept regarding that.
First option is true, sir.
Okay, so first option is true. Okay, I'm noting it. Anyone else getting different answer? You can post in chat or directly unmute and say. That will be more better.
Third one is wrong.
Okay, so third one is wrong.
Yeah, I agree. Third one is wrong.
Second one also wrong.
Second one also wrong. Okay. Anyone else getting about 4 option or regarding any option? Okay, so please explain why the first option is true. Who had said?
I had told first option.
Yeah, so
Two invertible means it is a maximum rank. The rank are equal for the both matrices. So it
okay.
is equal.
So they are equivalent. So yeah, so matrices are the same order and they are invertible means saying to be the both have that means whatever the order, if you assume the matrix, this whatever fall in this question, let's say matrix order of matrix is 3, square matrix there, because invertibility we are talking. So let's say 3, so rank of the matrix will be 3. So both matrices are invertible, that means both matrices have same rank, which is 3 3. That means saying to be both matrices are equivalent, because equivalency or rank will enough to tell you that both matrices are equivalent. And what about option 2? Who have said this option is wrong? Mohan Raj, he told us.
Base or not equal.
Me, sir.
Manish told, I think.
Yeah, yeah.
So you can, why these two are not equivalent?
Ranks are for rank are not equal, and like for B, if you we can say rank is about 2, because first one is the linear combination of second and third row.
First one is the linear combination of first and second, this one.
Yeah.
Okay, okay. So what is the rank of B then?
2
Two.
will be the rank.
And what is the rank of A?
Rank of A, 3, I think.
Okay. Okay, so yeah, rank of A can be obtained using, you can change it in row echelon form.
No, sir, if determinant is not 0, then the rank is 3.
If determinant is also not 0, then rank of A is 3, and you can conclude that these two are different rank, having different rank. So these two are
different.
Yeah.
Sir, my query is like looking at this, some of the questions, answers coming in quick. So typically how, sir, like let's say generally if you come across this question, what the first thing that you think is, okay, they're asking for equivalence, and then you go by the usual formula, says that, okay, if A is equivalent to B, then go and write down the formula saying that B equal to let's say QAP, A equal to QAP, QNP or square, then go and do the row echelon form and all those things. That is a long drawn process. It's a waste of time.
Yeah.
So how is it that some are able to say it immediately within probably a minute or so? So that is something which is which I thought, like, is there some other quicker way? Because doing the row echelon form, QAP formula, QNP invertible matrices, and then trying to find out finding out A and B, and then finding out Q. This very long process. It itself will take 15-20 minutes.
That is not a long process, because it's using only one concept about rank.
So what is the concept behind here?
That's all only the getting rank. So rank is like you can quickly do. Let me like I am doing here.
Yes,
176. Like let's find that it like finding the determinant is also very quickly you can get here. But let's say find the rank using using or changing it in row echelon form. So let's say this is 2, 1 and minus 1. So the way is to you will usually like getting the rank of a matrix, most probably use row echelon form, which is very easy to, like, when the numbers are bigger, when the entries are bigger, then more helpful using the row echelon form or reduced row echelon form. Now what will be the next? As here this is 1 here, so you will multiply. I am multiply with 2 and subtract from R2. This is R2, this is R1. So quickly you can do, like, this is 176 and this will become 0, and this will become minus 13, and this will become 12 minus 13. And next is again, just quickly do, just multiply first row with the 5 and subtract it to make it 0. Because row echelon form, hope you know that, making the matrix in upper triangular form. Yes, and below that it will be 0 kind of. And next is multiply R1 with 5 and subtract it. So it will be from R3, it will be 0. And this will become 35. Then this is
last column is plus 13. No?
No, minus 13 will be. Oh, here is.
Sir, this rank is connected to like matrix multiplication concept, and like it has to satisfy, no, sir, the order m by n is it is close to related to that one, sir?
Close to no, I didn't get. Sorry, can you repeat again? Huh?
Like how the rank is related to like equivalent matrices. Is it due to this like matrix multiplication we do, sir? Like equivalence AP is
Yeah,
equal
actually
to
the reason is like when two matrices are equivalent, when we are able to find a P and Q or Q and P such that we can write B as Q time A time P, and Q is actually when you write this matrix like see if you write matrices like let's say this is B here, and let's say Q is, if you are unable to find Q, so you can write identity matrix here 0 0 1 and write the matrix A and the right matrix again of that order. Let's say of that I am taking a square matrix. Otherwise, if write the matrix identity matrix of as according to the multiplication is as multiplication is defined. Again, write here identity matrix. Now try to change A in row echelon form.
Someone is talking. Please mute also. Sorry.
Okay. I thought maybe someone is arguing. Okay. Now change A2 in the, try to change A in the form of reduced row echelon form. Okay. When you change in reduced row echelon form, you will get Q and P kind of. Mean to saying that the existence, why this Q and P or rank is enough to tell these two matrices are equivalent. The reason behind this, in video sir have clearly told that when you change in the matrix in I cross n 0 0 kind of, and then equivalency is an equivalence relation. Because of that, this is we get the sufficient condition that if two matrices have same rank, then they are equivalent. So it is a intrinsic kind of like you will, this can be proved also. Sir have given a rough idea how to prove, but if you know only the rank, that's enough to solve the question, and most of the question will be solvable to using only the rank. So if rank of two matrices are equal, then you can directly say these two matrices are equivalent.
We don't have to find Q and P if
yeah, don't have to find Q and P.
If we
That's
are
why
just given the matrices, we can directly check for the rank.
Yeah.
So come again, sorry. So here, as what someone was remarking, for the matrix B, the third row. Sorry, the first one was a linear combination of second and third, if I'm right. Like that's what they are mentioning. So if that happens in any matrix, if you find that one of the rows is a linear combination of the other rows, then we can immediately say that it is the rank. I mean, it is
no. So anyhow, you have to calculate the rank. Then you can decide the rank.
No, then so okay. So if for the matrix B, we can see that the first row is a linear combination of second and third, right? So what does it signify like? So
it is not a matrix of maximum rank.
So again, here is the condition is again.
So here A and B both matrices have the same rank, so that.
So both matrices have the same rank, so they are equivalent. Is my calculation?
So the rank is 2 because how do we know that the rank is actually 2? So we know that okay, it's not going to be maximum because it's linearly. One of the rows is linearly dependent on the other two. So from that, so rank, how to get the rank 2 actually? Okay, it may not be rank 3.
So yeah, actually when we are calculating here, we are getting the rank or not, like this matrix have rank not 3, it have 2. And
so, my question is how rank 2 for B?
Yeah, so next one is, next one is you have to divide with 13. So it will be 1, 1 or
so
minus.
I'm not going to that, sir. I'm not going to that Gaussian elimination. That I know. That is the process which you follow. I'm saying by the look of matrix B, and the other fact that we just got to know that, okay, the third row is a combination of first and second.
Yeah, so that is like by
then
doing with
from
the
that
practice.
information, how do you get the rank?
That is you need to be like more practice, and then you will know. Like we have to again, like for me, if I am doing, so I will do with this process. Okay, let's find the rank. Now here you can decide that, okay, rank of A is 2. And again, now we have to go with the B. Let's see that what's happening. So this is
coming back to coming back to B. So the reason why the rank is 2 is because two of the rows are, the third row is a combination of the first two. Is that the case? Rank, how does probably the person who said that could clarify, because I thought that is an important point. So who was that who gave the rank as 2 just by reasoning it out that the third row is the combination of first two? From that we get the rank 2.
If you are able to see, otherwise the simple way is to doing like the finding by the writing way, like I am doing here. As let's change the here now the rows to make easier things. It will take time to be understood. Like if you did more practice, then it is easy to do. Otherwise, now this is 1 here, multiply with 2 in first row and subtract it here. So it will be 1, 1, 4, and again this will become 0, and this will become 1 here, and this will become 8, and this is minus 10 here.
Sir, option 2, then both A and B have rank 2, no?
Both, so yeah, I'm looking that both matrices have same rank, so they are equivalent.
No, but the determinants are not same.
Determinant are not same, that is not a matter. But yeah, they have the same rank, then they are equivalent. So this is 0, this is 1 here, and this is again minus 10. So again, you can from here, you can quickly decide that these are like same rows. So again, you will get. So actually, those both matrices are equivalent. And this is minus 10 here, and this is 0. So rank of B also 2, and rank of A is also 2. So they are equivalent.
Only rank is sufficient to decide about the equivalence.
Only rank is saying to, because suppose like why you will not go to calculate determinant. Suppose the order is 3 cross 2 or 3 cross 5. Suppose I am saying, then you are unable to get the determinant. Yes. Only way is you will use the rank of the matrix.
But suppose if there is the same rank but different determinants, still it is equivalent.
Okay, so no. If you compare two matrices, both have same order. Like I am saying, so I said okay. Let's say this is 3 cos 5, and both will be the same order. Okay. Yeah, but maybe not a square, maybe different rectangle. Okay. So now let's move on to next option. Is these two are equivalent? So here is best way, easy to decide, get the determinant, because only you can easily, because here is square matrix, so easily you can do, or rank will be, you can see that the second row is a multiple of the first row. So that means the rank of A, what says rank of A is 1, because this will become 0. You can do if row operation. And the second one is, they are not like here is rank of B is 2. You can quickly to see that both are independent kind of, or the second one is not multiple of first one. So this is 2. Now these two ranks are different of this matrix. So in such case, they are not equivalent. So this option going to be wrong. Now the next is about the fourth option. Consider two linear transformation T1 and T2. Okay. Let A and B denote the matrix representation of T1, T2 with respect to the standard order basis of R3. Then A and B are equivalent. So how you will decide this?
Do we have to form the matrix and then find?
Yeah.
Yes. Then find, yes.
And anyone else, like the best way is to doing this, just quickly find the matrix representation of T1 and T2, which is A and B, and very quickly decide the rank of A and B and just done. Otherwise, if you know to find the rank of linear transformation, so you know that rank of linear transformation equal to the rank of the representation matrix, whatever the represent matrix you got for that linear transformation, saying to be rank of A equal to rank of linear transformation, okay? Because A is the matrix representation of T1.
Yeah.
Rank of B equal to rank of T2. So if you know very quickly to find the rank of T1 and T2, yeah, transformation, then you can directly compare that, yeah, okay, A and B are going to be equivalent or not.
How can we find here the rank of the transformation directly?
Directly is if you know more, if you did more practice, then you can. Otherwise,
here
like
I'm getting the feeling that it is all full rank. Both are full rank. Is it correct?
So see, to find the rank of a matrix, rank of a linear transformation, the rank nullity theorem will very useful to decide that. Like here is we are working on the, but here, yeah, also with the note that ordered of the basis, what matrix representation, whatever you are taking, that should be a standard. Then you can easily do all the things. Like here, the standard order, like ordered basis is standard ordered basis. So best way is to finding that the represent this matrix, like what I mean to say, find the nullity of this linear transformation, and this can be very quickly can be found.
Okay. That is
sir,
easy.
both matrices have the same order. Rank is 2.
And then decide the rank using rank nullity theorem. So how we will find the nullity of this matrix?
Equate it to 0 and then find.
Equate it to each coordinate equal to 0.
Okay.
X plus 4y minus 2z is equal to 0, and minus 2x plus y plus z is equal to 0. And how, like whatever the nullity, if you are getting this, that is like whatever, how many, like this system have unique solution or no solution, it will decide very quickly. You can decide, and whatever the this null space of this matrix you will get, that is the nullity of T1. Similarly, you can get for T2. So what about for what you think? What is the solution of this system? It have unique solution or no solution?
Okay.
So, sir, can we say that if the rank of transformation of matrices are matching, then like those are equivalent?
Then matrices, whatever we are getting matrices, they are equivalent if they are same.
Okay. So, sir, finally, that we can consider two matrices to be equal. First one is like if QB is equal to QAP. First method is that, and second one is like if the ranks are matching. So these are the two.
Yeah. So yeah, first one is a very tough. Like it will take so much time to decide Q and P. The best way is just decide the rank. That's all. Please mute everyone yourself, or let me mute to all.
So, sir, in the
now you can unmute and tell, because there are some.
So, in case of similar matrices, sir, like what is the condition we go by the rank?
Yeah. So we will discuss. Next question on similarity.
Okay, sir. Okay.
So let me know what's happening. What is the rank of T1?
Both are rank 2, sir. Both are equal.
Both have rank 2.
Sir, I got second the rank of second T2 as 2.
And T1?
T1 as 3.
So okay, so rank of T1 is 3 and T2 is 2. So that means rank of A is 3 and rank of B is 2. So that's according to you, both are not equivalent. Anyone else getting different answer?
Getting both the matrices rank as 2.
Yeah, I got the rank as 2 as well.
Yeah, sir, I got both to be 2.
Both have 2. Okay. Yeah, so you can decide using this, solving this system. Again, similarly, you can decide. I'm leaving to you. That's all. Just a calculation is for you. The second way is
sir,
find the
we can
A and
So we can do it in row reduced form, right? Not use
Otherwise, you can find A and B and then change in using row echelon form, reduced row echelon form, change in using row echelon form, decide the rank. Otherwise, here you can just quickly decide. You can. Because of just note that the order is given a standard, then you are able to do with this kind of thing. If suppose a standard not given a standard ordered basis, so best way is to find first matrix and then decide, because then you cannot use it freely. This will not work. Okay.
Okay, sir. Does determinant play any role in deciding whether it is equivalent or not?
Yeah, determinant also used to decide. Like the case is when the determinant of A equal to 0 and determinant of B not equal to 0, what it means is, but the case is both have square matrices then. So suppose you are able to get determinant, because here is the case for R3 is there. So suppose determinant of A is 0 and B is not 0, determinant of B. So that means B have rank 3 and it have less than 3. That means saying to be both have different rank. And suppose both case have 0, then the best way is just now you have to use a row echelon form to decide the rank.
Got it, sir. Thank you.
Sir, just a quick clarifying my doubts. While X, Y, Z are getting transferred to like as per the condition, so this is basically the transformation of the coordinates of a vector, right?
Yeah, transformation of coordinates. Yeah, okay.
Coordinates of a vector, right? No? I'm just clarifying my doubt. Okay.
Yeah.
But sir, in questions, when we get questions something like T23 equal to 4, 5 or T12 equal to 3, 4. So whether those are vectors or those are coordinates, what are those?
Yeah, so like in such cases, surely it is given that, see, those are vectors only, and that whatever that value is given or T is given on freely use on standard ordered basis, that's why it is given. So that means saying to be those are, you can usually as a coordinate, you can use that. That is, those are vectors.
No, could you write, sir, like T23, T in bracket 2, 3?
Like this, let's say T is equal to 2, 3, it is something given
4, 5. Right. So here, whether these 2, 3 are coordinates or vectors, what are these?
No, so this is a vector. This is a vector. This is a single vector in R2.
In R2. What about 2, 3, sir? 2, 3?
This is also a single vector in R2. No,
okay,
don't mix up. No, don't mix up with the coordinate and vector. Vector means saying to be like a vector in R3 means 3 coordinates will come.
Okay, so that is one vector. That is one vector.
This is a one vector. Yeah, but here are this is a one vector. In one vector, in R2, 2 coordinates.
Sir. Okay, sir. And then, sir, I have one more doubt. So, are you going to discuss about change of basis and all, or should I ask at this point itself?
No. So, change of basis, I think, have done in the previous week.
Okay,
it
so
will
then I will take less than 30 seconds, sir. Like, sir, when we decide, matrix A, B, and P and Q. So, for P, we say that B2 to B1 change, and for Q, we say gamma 2 to gamma 1, right? But I think in one of the videos, sir has done gamma 1 to gamma 2 as Q. So that both are allowed. That is only my doubt. Whether both are allowed or there's some specific.
Yeah. So let me write that. Let's say T is a matrix from V to W, and for for V we are using beta 1 and beta 2.
Correct.
And for W, let's say gamma 1 and gamma 2. Okay.
Right. Sir.
And matrix A is with respect to ordered basis.
Yes, when we transform
beta 1 and gamma 1. Okay.
Yes.
For beta 1 is for domain and gamma 1 is for codomain.
Right, sir.
And matrix B is beta 2 and gamma 2. Means saying to be domain, for domain basis is beta 2, and for codomain the basis is gamma 2.
Right, sir.
Now writing to be like in equivalent form, this is beta 2. I'm writing like to remember that. So let's say this is Q and this is A, which is here beta 1 and gamma 1, and this is P. Okay. So the process is, see, this is for beta 2, and now let's say I want to find the matrix multiplication or image with respect to T. The best way is like let's say this is X here. So X vector is there in V and in a vector V. So it will be written in beta 2. It will express in beta 2. Then you will multiply with matrix to find the image. Let's say you want to find the image of a vector. So you have given a matrix. What it mean that you will change this matrix according to this beta and multiply. Then it will the same saying to be it is Tx. Okay. So that means here this is P. So you that what it mean that here will be beta 2 and here will be beta 1. Means writing to be expressing beta 2 in terms of beta 1. If you see video, it will very much clear.
Yes,
And
sir.
now as here beta 1, gamma 1, so here will be gamma 1 and here will be gamma 2. There is a relation like this beta 2, beta 1. Now see that this is here, this is here, this is here, and this is here.
Okay, so if I change gamma 2 to gamma 1, so will it be wrong, sir?
No. So gamma 2 to gamma 1, then that is not a Q.
Okay, that
Or
is
to
not a
getting
Q.
express gamma 1, gamma 2 in terms of express gamma 1 in terms of gamma 2.
Okay, that only I will get Q, right?
Yeah, then you will get Q.
Okay, so gamma 2 to
So
gamma 1 is wrong. Okay, thanks for clarification, sir.
so this is the formula to be expressing like this.
So we are expressing beta 1 to beta 2, you are saying.
Here is beta 2 in beta. Below that says you are changing beta 2 in beta 1. Like here gamma 1 in gamma 2. And this is our A.
Okay.
Thank you, sir.
So this is all about equivalent matrices. Now let's move on to a similar, when we will say two matrices are similar. So let's solve this example, then we will, while discussing, we will more clarify the concept.
Sorry, just a second. So when you say gamma 1 below and gamma 2 above, that is one down.
Sorry.
Gamma, yes, sir. Gamma, the notation. So
Here.
Q, yes. Q, gamma 1 and gamma 1.
Yeah, express beta 2 in terms of beta 1.
Beta. That is express the bottom one in terms of the top one. Right?
Then what it means that you will write whatever the coefficient you will find in terms of beta 1, you will write in vertically. That's the meaning.
Here just wanted to know which one. So the bottom one will be written in terms of top one.
Okay. So let's solve this, then we will discuss about the similarity, more concept in similarity. So let me know which option is going to be correct.
Last option is correct.
Second option is correct.
Last is correct.
Last is correct. Option 2 is also
correct, sir.
Correct.
Second is also correct.
First and second are correct, and fourth is also correct.
Okay, first is correct. Second is, all are option correct. Which option is?
First is wrong.
Third option.
First is wrong.
First is wrong. Third is wrong.
First is wrong.
First is wrong. Third is wrong. Second is?
No, first.
Second is right.
Second is right. Okay.
2 and 4 are right.
And 4 also. Okay. Okay. So let me one by one. Okay, one by one. From your side, I'm let me Goswami, you can, Atul, you can tell which option is correct and reason is also. From your side, I will listen.
First option is correct, and second option is correct, and fourth option is correct.
Fourth option is correct. So why first option is correct?
Because when we write the condition for similar matrix, then we'll get P inverse A.
P inverse AP kind of. So how you will sure that if A and similar, then how it will be for such case? For this case, what will be P inverse? See, this says A is similar to B. That means this one. Okay. So now what will be P in such case here? For this, in this case, you can decide using this one. Saying to be P means here P you know already for such for this using this this condition. So now for these two matrices, what will be P here? In terms of in terms of here, using this P, you can say.
We will put P inverse of inverse in the right hand side, and that P will become P inverse.
So P inverse of inverse will be.
And A inverse.
There will be P inverse. And here will be A inverse.
Yes.
Okay.
So P inverse of inverse is P.
Okay. So here will be P, here will be A inverse, here will be P inverse. So how you are concluding this? My question is, how you are concluding?
So it's similar to saying that, because if you look at the equation they derive, B inverse is equal to P A inverse P inverse, which is nothing but P and P inverse are inverse of each other, right?
So yeah, the best is, means you have this condition says you have this one. Okay, now you want this one. So taking, let's take inverse of both sides. This will not affect the any on this equation. Okay, so what it says this? It says it will be B inverse equal to, now inverse of this whole is what? It will change the order, like it will go this side, it will be same as it. What it means that if you have A B inverse, it will be B inverse A inverse. This is the mean. So that means it will be first here, and in between it will be as it is at the same plus, making to B inverse and this one. So it will be P inverse. Okay. And this is A inverse, and it will be P inverse of P inverse. This one. Is it I am making wrong, or
the first one is P, right? First one is
correct.
No, it is correct. Okay. The order will be changed. Order will be changed as here we are changing.
So that will.
So now it will be P inverse A inverse P.
So that will be P inverse A inverse and P.
P inverse A inverse, and this will be P again.
It is same then.
It is the same as we are looking here using the this according to this equation.
Then the determinant will be equal.
Determinant will be
equal.
Equal.
For inverse of matrix and the inverse of.
Okay, so let's I think I'm making a mistake. Let's see once again. We have P inverse is equal to saying to be A and B are similar. What it mean that B equal to P inverse A and B. We have this. So now take the inverse of both. It will be same as here. So that means it will be B inverse. And again, the order will change here. So it will be A P inverse, and here will be A inverse, and this will be P inverse. The inverse.
Okay.
So B inverse will be P inverse A inverse, and this will be P.
Similar.
That is correct. Okay. Okay, they are similar.
They are similar. That means we are able to get their exist. We are able to, and the same P will work here.
Sir, how come after P inverse A P whole inverse into this form?
As you know that A B to the whole inverse, what it mean that order will change B inverse A inverse. This is the property of matrices.
Identity.
Right.
So again, as here the whole inverse is then, so what it mean, and it will be shift here. It will be again, if you see like doing to or you can say like this one and then P, then apply inverse. So what it will be? P inverse A to the whole inverse. Okay.
Right.
Now it will be P inverse. Now this order will change. So
A
it will be
inverse
again
and
P inverse. Here is A inverse, P inverse here. So P inverse A to the inverse here.
So it will be, sir, P, na?
P inverse AP, yeah. So we are getting the same P as in the same for this case.
Okay. Thank you, sir.
Okay. Now, what about the second option? If A and B are similar matrices, then is A square and B square similar?
Yes, sir.
Yes, sir, they're similar.
So how it is you are concluding?
So you can take B square is equals to B into B.
B square is equal to B
B
into
into
B.
B.
Okay.
Then PAP inverse into PAP inverse.
P inverse AP
Yes, sir,
again
sorry.
P inverse AP. So yeah, as here it says, so it means B equal to P inverse AP. So we have this B equal to, we can write like this. Now B square can be written as B into B. Okay, so B is actually P inverse AP. So I just express separately here. Okay. Now P inverse AP, take these two, it will become identity matrix. Okay. So this is P inverse A, identity again A, and here is P. So now identity, as here it will become A square with multiplying identity. So final thing is A P inverse A square P. Here is B square. So again same P work for both as previous one.
Okay.
Okay. So we are able to get there exist P, the same P will decide that okay, these B square and A square are similar. Now what about this one? If A and A square and B square similar, then A and B will be similar.
I think reverse is not true.
So why? What is the reason? Or you can give an example which is not just satisfying here, this one. So let's do something with the property here, then we can decide. Okay. So property, what are the property of similar matrices? Both have same rank and
Same
both have
determinant.
same determinant and both have same trace.
Trace, yeah.
These three properties very much useful to decide.
Same what?
Same rank, same determinant, and same trace of the matrix. Both have the same traces. Okay. Trace means addition of this.
Sum of the diagonals.
Sum of the diagonals.
So in case of A square and B square, the trace will. Okay. Let's see.
Let's see that. Yeah, that's the. Let's see. Okay. So okay. So what it says, B is P inverse AP. So both have same determinant. Data of B is equal to data of P. So let's take a matrix of order 1 only.
B square equal to P inverse A square.
Let's take a matrix of order 1 only. Okay. So let's say 25. I am taking a matrix 25.
So can you put B square to P because B A square and B square are similar. Let's start off from that point.
Sorry, I didn't get.
Here,
I'm not.
The option A square and B square are similar. So we need to start from B square.
So we need a square. Both are. So as we know that both have same determinant A here. So we have to take two matrices. Okay. So let's say two matrices. Let's say I am taking A is also of order 1 cross 1, which is 25. And B is also, because determinant should be same, if you calculate determinant of this matrix of order 1, which will be 1. Nothing is like, there is no or rank you can say, or trace if you are saying. So this is, I'm taking A and B equal matrices. So this is similar matrices, you can say. What will be P here then? If you are, see, both have the same determinant, and I'm saying these two are similar. Why these two are similar? Of order 1 cross 1. What will be P here for this matrix A and B?
P will be 1.
Will be 1, right? Because one identity matrix, 1 of order 1.
1.
Okay.
P inverse also 1.
P inverse of P inverse also 1. Okay, so that means B equal to 1 cross 1 A, and we are getting A here and this one. Okay. Now what will be then A here for this? Sorry, this is A square. Sorry, I am taking A square here. I missed it. A square, B square I'm taking.
Yeah,
matrix.
yeah. Yes.
Now what will be A here then?
A should be 5.
A can be 5 or A can be -5 also, right?
Yes, yes.
And what about B?
Again,
B also can be 5 and or -5.
Yes.
So as we know that both have same determinant. So what says if we take A is equal to 5 and B equal to -5,
then they
so
are not
is
similar.
both are going to be similar?
Not similar.
No, because determinant are not same, different now.
Okay, okay.
So for a simple of order 1 cross 1, it is not satisfying here. Of order 1. Similarly, you can check for order 2, order 3, and or till order finite order of order n.
Okay, okay.
Okay. So this is for the, that's why the option 3 is not correct. You can using this argument you can tell. Now let's check for the fourth option, which is
The
here.
option can be checked same as the option 1, taking transpose both sides.
Similarly, again taking the transpose. As here we did here taking inverse. Let's take the transpose of that. That's
this
all.
is because since the trace for similar matrix is the same, so we will take transpose.
No. So still, if you are say using trace, that you will say traces are same, then they are similar. No, it cannot be also. Traces are same. Still, this says, see, if A and B are similar, this implies then rank of A will be equal to rank of B. Date of A will be date of B determinant, and trace will be equal to trace of B. But not this side. It will not imply this side. If these two are equal, still you cannot say they are similar. If these two determinant of these two matrices are same, you cannot say these two are similar. So there is a exam. There is an activity question on this. You can take it for why these two are not going to be similar. The last one in your activity, you can, if you check that both have same determinant, same rank, these two both have same determinant, same rank, and same trace, still A and B are not similar. You can prove it with the definition that B equal to P inverse P or A equal to P inverse AP. Using this one, only using this one you can decide. Please check for yourself. We can easily check that why these two are not similar. But yeah, in these two are following all three condition of the similarity. Like condition means result of the similarity. Both have same rank, same determinant, same trace. So please check. You can easily say that A and B are not similar.
Sir, in
So
this question we have given explicitly that A and B are similar, right? So
Here, how we will prove it is not similar, sir?
Using this definition,
B equals to P inverse
B equal
AP.
to P inverse AP or A equal to P inverse
BP.
AP. Using this one. That's
Yeah,
all.
if we take P inverse BP, we can see that P inverse into B will be P inverse itself, and multiplying that with P will also yield the identity matrix. So it will only be similar to the identity matrix itself.
Actually, the reason is A is some different matrix as B is identity matrix. So when you are saying to be A is similar to B, means A should be equal to P inverse BP, and where B is identity matrix. So if you multiply, it should be identity matrix. But A is different from identity. So how these two can be equal? This is going to be a contradiction. Assuming to be a similarity assuming to be a similarity. That's why you can say these two are not similar using the exact definition P inverse BP kind of.
Okay.
So similarity needed some more sufficient condition, and not only sufficient. Similarity is like in, you can say in linear algebra, deciding two matrices as similar is not easy. It is a very difficult. You need always to find P, or anyhow you have to determine P. But yeah, most of the time you can using these three property, you can cross the option and can tell this may be, these two may be similar. So using these three property you may decide, and using the next one, this definition also will help to decide.
Okay. Sir, for the transpose, what did you do for the transpose?
Transpose, yeah, same, like you have B is equal to P inverse AP. So take the transpose of this, it will be same as here, both side will be transpose will be equal. And again, if A, B transpose will be, means B transpose A transpose.
Same identity.
Okay. Same. Okay. So that's the till here for deciding. Hope many of you are getting what we are discussing. All of you, not many, all of you. Let's solve a next one question, which is on affine, and maybe it is a very helpful for you to maybe in end sem. And also, if you go on through mock, there is a question on mock and affine. So let's discuss. Today I will
more than one question.
So let's discuss this one, and maybe today I will give you a trick so that you can easily decide which option going to be true for the affine. Only using the basic definition, and you have to remember that definition. So let's do that here. We have this question, L and L prime be affine. This is your practice question, but we will do and we will briefly, or maybe main in comprehensive way, we will discuss this. So we have two affine subspaces, L and L prime. L is U and L prime is defined like this one. Okay. And U is here defined. U and U prime are subspaces of R3. And for U, basis is given this one. And for U prime, basis is given this one. Okay. Now there is a linear transformation also given between these two subspaces, which is from U to U prime. And the property of the linear transformation is mapping of this 0, 1, 0. U is here and basis of U is this one. And this vector is belongs to kernel of T, means what it means that this, when you take image of 0, 1, 0,
it is 0, 0, 0.
Okay, now the next is for the second vector, it is given image here. For the first question, image is given this one, and the second vector image is given this one. And these two are, if you said these two are the vector from B prime, basis element of, sorry, U prime. The first one and the second one, you can see that here. Okay. Now as we got T's properly here is defined, no issue. We have asking that F is an affine affine mapping, sorry. F is now an affine mapping defined like this. So what is remain to be, like if in this mapping everything is given, U is like a general vector. U is saying to be a general vector from U, the capital U. So which of the following option going to be true? Like find the affine, which is like same F will give, and which will be L here, and which will be L prime here. So and the definition of L is, please note that definition of L is given this is, and L prime is this one. Now to solve, and let me know which option is going to be for true for L prime and F. And let me remove
option
all.
2 is correct, sir.
Option
2.
Option 2 is going to be correct.
Option 4 is not correct.
Option 4 is not correct. Okay. I will ask the reason. Okay. Okay. I'm just noting here, but I will ask the reason after, let's say many of you decide that how the options are going to be wrong or right. Okay. And if you are, if you got any other option, please let me know also which option you are deciding right or wrong. In this question, almost all concept under whatever fall in affine is used. All concept whatever in the video lecture for affine.
Sir, option 5.
Option 5 is true.
Yes, sir. Option 5.
Okay.
Option 3.
Okay.
Sir, option is wrong.
Option? Which option?
What?
First is wrong.
Option
Okay.
2 is correct.
Option 2 is correct. Okay. Okay, so yeah, let's discuss maybe many of you will take time because yeah, it's time take you also. So yeah, before that, let me know, just like Mohan Raj said, Mohan Raj.
Yeah.
Like you said some options.
I told about only option 2 and 4.
2 and 4. So why option 2 is correct?
2 is defined by the U. The bases are 3 with 3. Cardinality is 3. Therefore, it will belong to R3. L also will belong to R3.
Belong to, not belong to, exactly R3.
Sorry, it will R3.
Exactly
then,
will be R3. Okay.
And L prime is defined by U prime.
L
which
prime is okay.
The basis vectors are only 2.
2.
Therefore,
So
it will belong.
it will not exactly R3. It will be not subset means a subspace of R3.
Yes.
Which having dimension 2.
Correct.
Not
Dimension,
exactly R3.
Dimension will be 2. Yes.
Yeah. So, and let me know from other. I will discuss one by one all. But let me know anyone who have said option 1 is correct. Why option 1 is correct?
Right. Option 1 is wrong.
Sorry, option 1 is wrong. Sorry.
Yeah. Actually, if we go for x minus y equal to 2z, it is a kind of subspace. I mean, x minus y equal to 2z is like a subspace of dimension 2. Or we can substitute the third basis 0, 1, 0. It will not give us a valid
Not give a correct. Yeah, that's the
answer. L is x minus y minus z equals to 0.
And somebody says L prime will be this one. So how you got this?
So for this, I first calculated u prime, which is the vector subspace, and that u prime was coming as x, y, z, such that z equals to x plus y. So for L prime, I took the 2, 0, 1 plus x, y, z. So likewise, I did for L prime. So my final answer for L prime was x, y, z, such that x plus y minus z equals to 1 after adding 2, 0, 1 plus u prime.
Okay. Yeah. So yes. So actually, for let me
First, we have to calculate the vector subspace for which the basis is given, and then we can calculate the affine subspace.
So yeah, before okay, that's okay. Fine to know, all of you know this affine. So that is a very good thing. So before that, what is affine subspace and what is affine mapping? So affine subspace, if you little bit know the definition, that's enough. Like in this video or for this course only, dealing with matrices R2 and R3 will be enough to know how this affine subspaces are. Let's see geometrically what is affine subspace in R2 and R3. So if many of you know, we've gone through the definition of subspace, and also there is a tutorial on subspace. That suppose this is R2 here, because as we are taking only in plane wise, and this is x-axis, this is y-axis. So R2, think R2 as it as a vector space with respect to addition and multiplication, as in coordinates wise and as in scalar multiplication. So R2 is a vector space. So possible subspaces in R2, what will be? It will be a line which pass through origin, or maybe a 0 origin also, or whole R2. So possible subspaces of R2 will be maybe a 0, 0, may not maybe 0, 0, and a line which pass through origin and the whole R2. There are three possible subspaces. Now affine subspaces says, in geometrically I'm saying, let's say this is a line which passed through origin. Okay, so it means it will be a subspace, or it is a subspace of R2 with a geometric representation. If suppose you are able to write this equation of line, let's say this will be y is equal to mx. It will be not added c here because it passed through 0. So only y is equal to mx will be here. So equation of this line is, let's say, y is equal to mx. So affine subspace corresponding to this subspace, or a subspace which corresponding affine subspace which correspond to this subspace means a line which parallel to this line. So let's say there is a vector here, or let's say there is a vector. So I want to find a affine subspace which correspond to this subspace means there will be a shift. If you shift this two parallelly to this one, so this will be a affine subspace of affine subspace of R2, which having subspace of R2 is this one. Corresponding subspace, if you know the word, what it means that L is equal to, let's say L is equal to, and this, let's say this is vector AB here as we did here. And let's say this we are denoting U. So affine subspace, what will be writing to be L equal to this vector, which is AB, plus we are denoting this subspace as U, which is Y is equal to MX. So let's say this U is here. So this is an affine subspace of R2.
So L is new subspace, right, sir? L is new subspace.
U is subspace. This line is U.
No, L is new subspace.
L is not subspace.
It is not a subspace.
Affine subspace, right?
Affine subspace. Okay, yeah. Okay. This line will never a subspace. Why? Because if you see that this line is not passing through origin.
Does not pass through origin. Yes,
yeah. And what it mean that if you there is a subspace, it means that in which in that subspace 0 should be there. Zero vector. But in this, if you geometrically, if you see that there is not 0 in this line.
Yes.
So this is an affine subspace. U is also itself a affine subspace. If you want to write like this definition, then how it will be? U equal to 0, 0, or sorry 0, 0 plus U itself.
Yes.
So that's all. This is the saying to be affine. Affine subspaces are shift of the subspaces of the geometrically. You can see that this is happening. Let's say this is happening in a system of linear equation. So system of linear equation, let's say AX is equal to B, and you are able to get this system has a solution. This system, suppose this system has a solution. So the corresponding subspace, like as here we are corresponding subspace getting U here. Solution of this system give a affine subspace. And the corresponding subspace, what will be? Null space of this matrix. Because you know that null space, null space of a matrix, you know, rank, row space, column space, you know, as like that you have gone through if week 6 or something. There is a null space of a matrix also. So solution of a matrix give an affine subspace, and the corresponding subspace of that affine subspace is actually the null space of only this A matrix. Similarly, there is a concept in R3 also. Very similar concept. Suppose this is R3, forms a, this is vector space with as usual, you know, coordinate y addition and multiplication of scalar is coordinate wise. So, and this is a vector subspace R3, and let's say this plane is passed through origin. So just if you want to find a affine subspace which pass through this vector A, B, C, that means just shift this plane to here parallelly. That is, this plane is an affine subspace of R3. So same as here. Shifting of that in as in R2 is happening in R2 is happening very similar to in R3, and here is also very in the system of also happening. The what will be the affine subspace here? Affine subspace here, it will be any take a solution. I'm saying solution is exists. Let's say solution is alpha prime or alpha. So affine subspace will be alpha plus nullity null space of A. This is the corresponding. This is the affine subspace of R3 regarding this system of linear equation. You will see when you solve a question on mock, there is in mock there is a question on this concept, on this affine. So if you know, if you want to know this, just see this video. Sir, have please see this here. Very note sir have written. It is enough to tell you this one.
Sir, in the mock, I have a little doubt. Can you solve it?
Yeah, we will discuss. Let me finish this. Okay.
Yes, sir, complete this first, sir. Complete this.
So if you see this one, this is regarding the system of linear equation and talking about affine subspace of which is related to the system of linear equation. So if you come to the first b equal to 0, that means homogeneous system of linear equation. And in such case, null space of A is RA, here it has denoted, which I don't know in name wise. Let's say this is RA, or you can say this is NA also, null space. So if you suppose B not equal to 0, this give a affine subspace. Solution of L will be a solution of this system will be an affine subspace of Rn, and L, which is L, will be V is a any solution of that system, a single solution, because this system has infinitely many solution or maybe unique solution also. So take a solution and add with the null space of it. That is the corresponding, you can say, related to the system of linear equation, affine subspace, this one. So you will, when you see the mock question, you will know that what is happening, and that can be solved using this concept. That is very much helpful. So if you spend time, you will know. Otherwise, that's no matter. Yeah, let's discuss this question. That's all about the affine subspace. And next is this is about the affine subspace is done. Remain to we are remain affine mapping. So again, as you know, T is a linear transformation from a vector space to vector space, V2W. Now suppose we want to find a mapping from affine subspace. See, affine subspaces are not a subspace or not a vector space. That is a shift of a vector space. So we want to find a map with the related to the affine also. So that map is called affine mapping, nothing else. Like here we are saying linear transformation. This may not be a linear transformation. Okay, F may not be, maybe also, and may not be a linear transformation, as L is not a affine. Sorry, as L is not a vector space, as here is happening, L prime also. So F may not be an affine, but the relation is here with F and T. Okay, F and there is a relation in linear transformation and this affine mapping. What is the relation? Relation is the same. Let's say now I'm changing it here. The same thing I will use. Okay, L corresponding to correspond to here same word. Let's say using this one. This is U and this is U prime. Okay, this is U and U prime. So U is corresponding subspace of L, this one, and U prime, this is U prime. U prime is corresponding subspace of L prime. L prime is affine subspace, and there is a map T, which is a linear transformation, is given. So I want to find an affine subspace. So affine says take a vector as here L is B plus U, L prime is B prime plus U prime, let's say. Okay, so affine mapping is writing to be V plus U. Let's say U is XYZ if you are dealing with in R3. So at XYZ, this should equal to B prime plus T of XYZ. This should happen. Then this F is an affine mapping, you can say. See, there is a associated linear transformation. Now let's say somebody is given, there is no information about T. Somebody is asked like this. You have a mapping, let's say XYZ is equal to defined like this. Something is defined. So is this map is a affine subspace or not? So let me show the video first. Here you can see that I am not making any different, same argument I am going as sir have gone. First one I just now discussed about this one, f b plus u equal to b prime plus tu, where u is, you can think x, y, z. Just I read for convenient or your for simplicity I just wrote here. Now suppose your map is given as here in the now let's back to the first definition. F is given, we want to check this f is a linear transformation, this affine mapping or not. So what is the condition? If you read one by one, you will reach here. And if you say that the condition says fu plus b minus fb, which gives a mapping G, this map should be a linear transformation. What it mean? I will solve using this definition, these questions. Okay, what it says this: take a image from L, let's say a particular vector, let's say v prime I am taking, and so image will be this. Let take a vector from L v prime, no v, particular vector v, so image will be fb. Okay, so if you want to find, if you want to check f is a linear transformation or not, so take check like this: f of v plus x y z, okay, minus f of v. It give, this equation give us some x y z terms will give. Now check these terms, means this mapping, this final thing is, as in video this is gu. If you suppose this is u, so this is gu. So is gu, which give this side, is a linear transformation or not? If it is a linear transformation, then you can directly say this map is a affine mapping corresponding to the but surely it is given as here t. T should be surely given somewhere.
Sir, what is xyz here?
XYZ is a single vector u. Sorry, see, u is single vector. This is saying to be a single vector. I am dealing with in R3. That's this is a like a general vector. This is
so offset vector. Because of it is affine plane is offsetted.
Okay. So now let's when we will see this much I told you, I don't know many of you will not get. While solving we will get this. All things I will solve with one by one. Whatever I just now said, this f about the f, one by one I will solve. Okay, so let's do this one. So let's in this options, if you see the options said we need to find L and L prime. So L is u, exactly u, and u is, for u basis is given. So basis is, in the basis 3 element is given. So what it means that dimension of u is 3.
Correct.
So that means dimension of u is 3. Then what is what will be u, means what it says u, and you know that dimension of R3 is also 3.
Yes.
So that means u is exactly R3. No need to evaluate here. Using the cardinality you can decide.
Correct.
So the dimension of u is equal to 3 without row reduced form. How you find it?
See, dimension is 3 because this is the basis, right? It is said this is the basis. This set is basis of u.
Okay.
You no need to check the determinant of this matrix, because it's clearly written that this set is basis of u. That means these 3 vectors are actually linearly independent. Okay, so you can directly say that L is exactly R3 as dimension, if you know. Now remain to now let's find L prime. L
sir,
prime is
L sir.
L
How
prime.
about L? How about L?
L is just now I discussed. L is actually u is actually says R3.
Fine. Sorry.
So let's find now L prime. So L prime is 201 plus u prime. So that means we need to find u prime, and basis of u prime is this one. Now let's back to our options. We will do it by options, enough to solve. Okay, we have given this u prime, basis of u prime is this one. Now how many u prime are here? These 2. Okay, One is says R3. You can directly cross it again. See, this is a basis, and in basis only 2 element is given. And L is, if you check that in this L says R3 exactly equal to R3. So what it mean there? Dimension of, not dimension. Here is not the word for L prime. Dimension means, now here you need to find a subspace of L prime, right? Sorry, corresponding subspace of L prime, right? Because dimension word is used for subspace, not for affine. So let's make out from L prime a subspace from corresponding subspace. So if you come out from corresponding subspace, it is actually the same R3. R3 says, it is says R3, and corresponding subspace of R3, see, L prime is R3 and dimension of R3 is 3. Sorry, I mix up. Let me one minute.
U prime is the subspace, sir.
U prime is the subspace. Correct. And if you try to find from here U prime, it says R3 itself.
Oh, sir, 2. It is our dimension is 2.
No, from this option I'm saying. This option I'm saying.
Yes. Yeah.
So it says U prime exactly R3, but here is dimension of R3 is 3, and here is dimension, as you know, here a dimension of U prime is 2. So it can never be.
So that is wrong.
That is wrong. Okay. Now we still remain to find U prime. So there are 2 ways you can find express way, like what will be U prime? U prime is the span of one span. Writing to be span means like this 0 1 1, and
here we get Z is equal to X plus Y.
X and Y belongs to R. This is the span. That this is the U actually. Span means span of basis, means this is the mean of span, right?
Yeah.
Now this is the mean of a span. So we have only single L prime. Okay. So see, from a given expression, hope many of you last time I took the session, if you have like this is given, then corresponding subspace what will be from here?
X plus Y equals
minus Z is equal to 0. Right? Because the shift, this is the shift is given. So corresponding subspace will be, it should pass through origin. So that means put right side 0, then it will be, that is the mean of corresponding subspace. Right?
Okay.
So this is the corresponding subspace. Now you know this is U prime. This option says this will be U prime.
Okay.
X plus Y minus Z is equal to 0. Now this option says this is U prime. So check this should satisfy. This should satisfy this one. This equation. So check that is both are satisfying or not.
It is satisfying.
Both are satisfying. So that means expansion or span of these 2 surely will be this one. Okay, surely, because
sir, I don't get it, sir. U prime, it is talking about the L prime, not the U prime.
So this is L prime. L prime. So I am saying what will be the corresponding subspace with respect to this L. This forget about this one. Forget about it. You have this is an affine subspace, right? Any line in R2 or in plane.
Yeah, correct.
This is an affine subspace. Find the corresponding subspace. What will be corresponding subspace? Substituting equal to 0. That's all.
Right.
So it says this is L prime. So what will be? That means this is U prime. This should be U prime. So check that it is satisfying or not.
Correct. U prime is satisfying.
So satisfying. That means if you expand this one, this will give surely this one. We can check that here also. Easily you can do also. How it will be? X, and this will be, if you solve this term, what will be?
Y.
X, Y, and X plus Y.
X plus Y.
So
sir, but sir, in this approach there will be a problem if it is said that X plus Y minus Z is equal to 50.
50. Okay.
Okay, then this equation is not satisfied.
Let's make it 50. Okay. So still you can you can find the corresponding subspace, which again will be the same. This one.
But if we just write the equation, so equation of the L dash is coming as
so it still is remain. See, from here you can directly check, but it still remain this one. Now next is so like
yes.
you check that, okay, but there is one another thing you have to check if you want.
So I check this one. So this one, so this condition will not be validated.
This will be not valid for when you check for this, because this is also a vector from L prime, right?
Yeah.
So you need to check the L prime. Otherwise, best way if you are mixing with the, so let's find the U prime, exactly U prime, and this is the expense. Now this is the span of these two element of basis. So it is like we want to find a relation kind of in X, Y, and Z. So how we will find? Assume this is capital X, this is capital Y, and this is capital Z. So what it mean that capital Z is equal to small, like what it meant, X is equal to capital X, Y is equal to capital Y, and Z is equal to X
plus Y.
Y. So it just substitute here. What will be here? Capital X plus capital Y. So that means the relation is capital X plus capital Y. If you want to write it like in expression form, so final thing you got X plus Y minus Z is equal to 0. So like you got the relation in between. So from here you can, now let's find the L prime now. See, then what it mean that U prime is equal to X, Y, Z, satisfying this equation. You got U prime here. Now let's find L prime. So what will be L prime? L prime will be
201 plus
201 plus U. So what it mean that X plus 2, Y, Z plus 1.
Right.
Satisfying this equation. X plus Y minus Z is equal to 0. Okay.
No, it is satisfying X plus Y minus Z equal to 1.
Now again you want to kind of relation. So assume again same. This is the best way to finding, like assume this is capital X, this is capital Y, and this is capital Z, and find the relation. If you try to get the relation, it will be X X plus Y minus Z is equal to 1 will give. If you again same putting same as here we are doing. Okay, as here again assuming to be, it will give this one. So that means L prime will be X, Y, Z such that X plus Y minus Z is equal to 1. So finally you got. Otherwise, if you want to go with option also, you can check one by one.
Okay, right.
Sir, with the help of option 3, right? Like the original equation is X plus Y minus Z equal to 1. Can we find the basis of L dash L prime?
Also see, that's why I want to, that's why I see extract the corresponding subspace, which will be X minus Y minus Z is equal to 0. To find the basis, you need a corresponding subspace, then you will find the basis, not for affine. Affine is not a subspace. You have to find the corresponding subspace and then find the basis.
Basis of that subspace.
That subspace. Not exactly that L prime. Okay.
So then can we say that, sir, affine mapping is between is a mapping between two affine subspaces?
Yeah, that's why I written. Affine mapping is mapping between two affine subspaces. Now see, this much you know to finding L and N prime.
So option 3 is correct.
Option 3 is going to.
Then how to confirm option 1?
So option 1 is about L. So L is actually we got R3.
No, that is wrong, right? Option 1 is wrong.
So option 1 is, yeah, because L is R3.
Because it is appears like a
two dimension. Yeah, 2 dimension. Appears like a 2 dimension. Corresponding, if you extract from the subspace of this L.
And we can also substitute the basis there and check whether that equation is solved.
No, yeah, basis, but see again.
So can we apply the basis and check?
Corresponding, first find the corresponding subspace, then apply the basis.
No, here in this case, the subspace is same as L.
Same, yeah. Then you can, yes.
Therefore, we just apply 201 there and see whether the equation is satisfied.
Yes.
So here 1010, it is not satisfied. Okay. Is that right?
Yes,
Yeah,
yes, this is correct.
yeah.
Okay.
Sir, for option 3, you took a shortcut or like what? Sir?
Other two ways I said. Otherwise, see, this is a long way you can find. Otherwise, shortcut is extract the corresponding subspace.
Yes, sir.
The corresponding
Zero
subspace is
shortcut, right? So
just write to be minus z is equal to 0. So this is going to be the corresponding subspace. Now check the bases are satisfying or not. Also check this one also for this L. First check this one is satisfying or not, this vector in this one, and then extract the corresponding subspace from this, and then check the basis also.
sir, this is the case when we have these things in the option, right? So what if we don't have these things?
Sorry.
So here we have these things in the option. So what if we don't have these things in the option? So
Suppose so the thing is you have to then you have to go and find the exact L prime.
In that case, we will find the transformation matrix and pass on some vectors.
So it still remain to see. This is for finding L and N prime, but most of the question having this transformation not is the affine mapping. So let's do that. That is also can be done very easily. The thing is only you have to find this T. Once you find T, you can easily decide which will be F. Okay. Let me tell you. So first let's find T here.
Right.
The finding T is the week 6 portion, right?
Finding T is all week 6 for previous one. So you have okay.
After this question, can you please discuss the yesterday's mock? There is one doubt.
Oh yeah, sure.
When will the answer for the mock test be released? Will be
in next 2-3 days.
Oh, okay. Yeah. Thanks.
Okay. So you have okay. Let's quickly do. Otherwise, time is going very fast. Okay. So we want to find a T in the expression form x, y, z kind of. Okay. So assume let take vector x, y, z from U and apply T on this. That's the best way. So okay. So if you find a vector, if I took a vector x, y, z, so the images given according to the basis, this one and this one. So that means you have to x, y, z, you have to change this vector according to the basis. What it mean that? Let me alpha means express this vector according to this basis. 2, 0, 1 plus beta time 1, 1, 0 plus gamma time 0, 1, 0. And what is mean? When you apply T here, then it means says alpha time T 0, 1 plus beta time T 1, 1, 0 plus gamma time T of 0, 1, 0. So as images is given, this is 0 because curve belongs to kernel. So let's find first one is given 0, 1, 1. So alpha time 0, 1, 1 plus beta time, this image is given 1, 0, 1, 1, 0, 1 plus this is 0. So gamma time 0. 0 means 0 vector. So that means alpha, that means 0 alpha alpha plus beta 0 beta. Okay. So this is T of x, y, z. So T of x, y, z is equal to beta alpha alpha plus beta. What it mean that we need to find alpha and beta in terms of x, y, and z. Okay. So how we can find? Equate these two as here is given. So just equate here. So it will be what it gives.
Alpha equals z.
Alpha equal to z. What's
beta
happening?
Equals x minus 2z.
Beta is equal to x.
X minus 2z.
How alpha is z? Alpha is y, na?
Alpha is y, right?
Alpha is y. Just equate and let me know what is happening. Alpha is equal to y. Beta is equal to something x, I think.
So x, y, x plus y.
X, alpha is equal to y. Okay. This is correct?
Correct. Yeah. Alpha
beta
is y, beta is x.
Okay. And z is?
alpha plus x plus y.
X plus sorry, gamma is equal to
What we are equating? What we are equating?
this one, right? This one. See, I just express x, y, z in terms of the expression.
Right. Okay,
according to basis.
Okay.
We need to find alpha beta. Then we can substitute just directly.
Yes. Then alpha equal to
No,
y.
sir, this alpha equal to z and beta equal to x minus 2z and gamma equal to
Alpha
y
is equal
minus
to z, beta is equal to minus
x
z.
minus 2z, x minus 2z.
X minus 2z, yeah.
And gamma equal to y minus x plus 2z.
Y minus x plus 2z.
Here it is different, no? The expression which you have arrived.
No, it's not same for last one. It's a difference calculation.
Okay, different. I think it will come x minus z. Please check yours if you check that. And
yes, sir.
Yeah, it will come x minus z. And
no, sir,
the
it
next
will
one
be x minus 2z only.
X minus 2z. Okay, x minus 2z will be, and beta will be x minus 2z, and alpha will be sorry, just a minute. Let me see. Your beta
will be x minus 2z.
X
alpha
minus
will be
2z.
z.
Alpha will be z.
And alpha plus beta is x minus z.
Alpha will be, and gamma will be alpha plus
x minus z.
X minus z. Yeah. Yeah, you can check that.
Yeah. Yes. X minus z. That will be x minus z.
So that means your t will be here. X minus 2z, and alpha is here z, and alpha plus beta is, what will be alpha plus beta? It will be
x minus z.
X minus z.
X minus z will come, yeah.
No, sir, it will be something.
X minus 2z minus x minus x minus 2z, which is x
minus z, correct?
Yes, correct.
X minus z, yeah. Yeah, so please check what is happening. This is not a tough question. You can easily calculate. This is just a
the G method that
in this question, gamma is not contributing because of 0, because we are getting gamma into 0, 0, 0. That is about gamma's value is y minus x plus 2z.
Gamma is equal to okay, whatever will be, just this is not a confusion, not a different thing. You only just need to find alpha, beta, and gamma in terms of x, y, z. If you compare, very easy to solve. That is not a big thing. Okay, I want to listen from your side. That's why I'm not solving.
Last option is correct.
Yeah, so actually the t will be exactly this one. If you check,
yes.
t will be this one.
Yes.
Option 7.
So okay, this one is going to be. So you got t. Okay. So now what will be? Now need to still remain f. So as just now said, f is equal to v plus u minus f of u, f of v equal to, this is t. As just previously we are discussing, that is gu here kind of. Let me show you a video first. This one, gu equal to f of v plus u or u plus v minus f of v. So this will help to decide g. It was g, so your g is actually your t here, linear transformation. So check that which one is giving t. That's all. Which one is giving t?
T is the seventh one.
Seventh one.
Seventh one is T.
Okay.
So
but it is directly coming fxyz is equal to x minus 2.
So yeah, that's the problem. It is directly coming.
No, so f will be, you have to add the vector 201.
So f will be,
if you add the vector 201.
Option number 5.
Then
yes, option number 5. Option 5 will be.
Number 5, you add 2 to the first one, 0 to the second one, and 1 to the third one. So you get plus 2 and plus 1 there.
Then option 5.
Option 5.
Yeah, actually, see what is happening here. So if you want to decide, see, one thing I said this one, or there is also said that f of v plus u equal to V plus TU.
Yes.
U is your small xyz here working as a general vector xyz. So what is your in this V? Sorry, B
Sir,
prime. So what
yeah,
is
V
your
prime.
V in this L? What is your V? 0, 0, right? So
Yeah.
that means f of u.
Correct.
And what is your V prime? 201.
Yeah.
Plus your T, TU. Okay. So that means f of x, y, z. U is x, y, z. X, y, z is equal to 201. Plus T is your x minus z, z, x minus 2z, and x
minus z.
Minus z, I think. Yeah. So now just add. So final thing, what will be? It will be x minus 2z plus 2. So f of x, y, z equal to, and it will be z. If you add this third second coordinate with second, it will be z as it is, and third coordinate with third. So x minus z plus 1.
Correct.
Okay. Otherwise, see, if once now let me tell you a trick.
Sorry, sir, one question. I got lost in this beta is equal to x minus 2z. I mean, if you can just point out from where, just point out the equation, I will do it, but from where did this come?
Beta, see, from this one, you need to clarify, decide what will be alpha, beta, and gamma.
You have to calculate from there.
Yeah, from this one.
So comparing both.
Actually,
Just
gamma will be a
comparing.
bit different. So yeah.
Whatever maybe I made wrongness. Yeah, maybe you told. Just clarify, but yeah, I am sure that this will be T.
Okay, sure.
Okay.
Yeah, thanks.
So, sir, what you have said that if V plus U equal to V is 0, what from where you got V is equal to 0?
Why V is 0? In such case, why V is 0? Because exactly you said here. So what will be your V here? Actually, any affine subspace V plus U. But here
so
is exactly your U as here.
Okay,
That's why V means here 0 plus.
Okay.
Right? 0 means 0, 0.
Okay.
And but here V prime is different, 201. So you can decide. Okay.
Sir, going by mock, it seems that there will be more weightage on affine space and affine subspace and mapping. Is it true?
Not more weightage.
Yes, of course. 3 to 4
maybe there is a question or related to affine. That's all.
So you're telling about some shortcut. Can you tell that?
Yeah.
This is the shortcut.
Yes, so shortcut means shortcut means from here, if you substitute 0 here, means what it means. What I mean to say, if you want to find this, see here is missing up. Just 1 minute. See, I want to say your T will decide F. So T you got this exactly. If you see that this one, and this one.
Yeah. So from here I can just subtract 201, like F000.
Yes.
Then that will be T. That is like from that I can understand.
Just neglect that constant part from all. You can decide.
So I can so I can reject option 7, but between 5 and 6 I have to check the transformation.
I can add that vector into transformation.
Because if say 7 is not a affine mapping, because if I subtract 201 from there, f of 000,
actually see, I will not say about this one. Just remove this. It will, actually it may be affine, because we are talking about for this question it may not. Sorry. For this question, for this question it may not. Otherwise, see, I want to tell you, see, there are some constants. Just remove those constants from those coordinates. That will give T, and if you are able to find T, directly check that option. That's all.
So option 7 is directly T.
So here we are removing the constants, that is 2, 0, and 1, because the V that I'm like f of V plus U, the V is 0, 0, 0.
Yeah, because of V is.
Yeah, if V is something different, then I have to check. I have to remove that V of that. like f of that.
No. This side, see what is happening here. Here v0. Let me tell you. Suppose this is kind of. Yeah, actually for that I needed a different question because here v is 0. See, suppose
like in the expression that you have written, like f of v plus u minus f of v is equals to t of u. So
T
here
of u,
v 0 0 0. So what I am doing is that the expression that is given is f of v plus u.
Yeah, correct.
Minus f of 0 0 0. If suppose v say 1 1 1, then I'll remove f of 1 1 1 to get t of u, right?
Yes.
Yeah.
But sir, over here we are not considering the 201 from the first line. We are considering the 201 from the last line, which is given as fu equals to 201 plus tu. So that's why we are adding
Actually,
that 201 to that.
in the mock, the v was not 0 actually. So that's why I'm asking.
In mock maybe v is not 0. Then you need to be. So let me show you. Then it will be.
Sir, the best method is to find the transformation pair.
First, see, from after finding the t, you can easily what I am saying. Just forget about the constant from right side. You can easily decide. Remove the constant. Okay, whatever the inside, if you forget about those, let's say this is kind of 1 plus x, 2 plus something, z plus whatever is, no matter, but just remove right side from the constant. This constant term from the right, it will actually give your t here. And you already found t, then you can match what is happening. Is exactly t is giving or not? If not giving, then that option will not correct. Otherwise, it will be. Otherwise, if you want to go with exact method, this is the.
Sir, in the whole problem, out of 7 options, if you select even one option wrongly, the whole thing is gone.
Yeah.
So what I am requesting, what is the first pass identification of sure shot right answers? What is the easy way to really follow through?
So, yeah, actually, I bit confused also here, but yeah, be sure with this one. Yeah, so for final thing is just decide with the final this finding u and just put in f of u and find, like you already found t. Okay, so now just find f of u, which is defined as 2 plus 0, and finally try to find f of u, which is in this form is given. So then you can check your option. Okay. Okay, so this much I want to tell you. This may be helpful for you to decide.
Yes, it is very helpful.
So let's move on to
mock. Please discuss mock, sir. Yesterday's mock.
okay, mock
last
can
question.
be mock can be
Sir, mock solution will be uploaded too.
Mock solution. Mock solution. Then that is more better. Like once you try, like there is a next session also next week. So in that also you can decide, because yesterday just now mock is done, like mock is released. So try yourself, then that will be more better. Once you try it, then you stuck somewhere, then you can ask or ask in discourse and try to solve yourself. Then it will be more. If I will discuss, if you done, then okay.
Sir, can you explain mock question number 5?
I can do that. Yeah, but solution is, let's leave the solution maybe next in next revision. That can be done, and also you will get solution. I just try to yourself, then you can ask in the last session also, because just now mock is yesterday done, and I am seeing that only 35 students have done, only 35 or 37. I am leaving to you also. Many of you, if you solve that, that will be more better. 5. Where is 5?
Sir, I have solved this paper. Okay, so my feedback was that paper was bit lengthy and somehow we forget many concepts. Maybe means that was the problem I found.
Yeah, paper was a bit lengthy. Yeah.
So let me discuss only the question 5. I will not going to discuss solution. The question is, just now I was discussing about a fine subspace regarding the linear transformation. let me, video is somewhere maybe. So I was discussing affine subspace regarding the linear transformation. So what was in that? If AX is equal to B, so if there is, and this system has solution, then solution is actually this solution of this system is actually an affine subspace, and the corresponding subspace of that affine subspace is null space of A. So what it mean that dimension of that affine subspace is, or you have also gone through the video, dimension of affine subspace is dimension of the corresponding subspace, or maybe the and corresponding subspace. So what is here asking for the dimension of V1 is corresponding subspace of A1, and V2 is corresponding subspace of A2, where A1, A2 is the solution you can say, and solutions are nothing but the affine subspaces. So asking for the dimension of what it means, then what is needed to find for you?
Row reduce equivalent form.
Yeah, row reduce equivalent, and I got
find the null space of row is long.
Yeah.
Okay, find the null space of it.
Yeah, but the thing is, I got the exact opposite of the answer which was given.
Yeah, right. B1 has dimension 2. This is the second option.
No,
is what I got.
because you are finding the rank, you have to find the number of free variables.
Yeah, number of
the rank
not
is
rank, not rank, not rank.
It is the number of free
null
variables.
space. That's why. That's why. See,
Okay,
please
got
note
it.
with the
Yeah,
null.
I think we put the same.
So the dimension of dimension is a number
It is
of
the nullity. Nullity you have to
nullity. Okay, fine.
Yeah, thanks.
It is the
Yeah,
dimension
so
of independent variables.
independent variable, because yeah, because that is the dimension of null space of A.
Right.
So be careful with that. Okay, so and in the fifth also, and the next question asking for the linear transformation. So again, you can see there is a 2 plus V kind of thing.
Yeah, so I was asking in this that the left hand side it was a 2 0 0 vector.
So actually that is a V is given, not V is 0 here. So that means here is you can assume X, Y, and this one. And if you remove the constant term from each one, you can see that which option is going to be correct. If you see that all options are different from the right side, if you remove the constant term, this is minus, this is plus, and this is plus, minus, plus. All options are different. So what it means that if you find a T, that's enough to decide which option is going to be correct. Here is very similar. You are in this option T, and you are sorry, the 7th option and 5th option are very similar. But in here, if you see that all options are different, what it means that if you remove only the constant term, it is actually that T will give, and you can check that option because that is the T. Okay. And this is actually V plus U. These are the V plus U, and this side is B prime plus U. That's all. This side is V plus U, and this side is V prime plus, sorry, B prime plus TU, sorry, TU. So if you remove that V prime, that means constant term, it will be T. It will be T. That's all. That's why I'm saying to always remove the constant, and exactly it will be T.
Sir, here the matrix representation is given by only -1 0.
So actually, because of the dimension, if you see that dimension for codomain is 2, and dimension for dimension of dimension of domain is 2, and codomain is 1. So here is matrix representation is given.
Only it is just a 1 cross 2 matrix, is it?
1 cross 2, 1. See, if you have a matrix, let's say 1, 2, 3, 4. So it is given like this, and bases are, let's say 1, 1, and 1, 2 for codomain, and 1, 0, and 0, 1 for for domain, and this is for codomain. So what it mean then? What it says that matrix representation of T is given. What it mean then? Image of 1, 1 equal to what will be? From here you will have to find what will be
1 into 1 0 plus 3 into 0 1.
0 1, right?
And T of 1 2 is
1
equals
0
to
3 times
2 into 1
0
0
1.
2
plus
into
4
1 0. So you can solve that easily. You can get, right? So now you can try to find in t in x in terms of xyz or in xy. So please be careful with these. Please try to know the definitions. Okay. So let's solve the next
Actually,
question.
we are more habituated with complex matrices. So minus 1 0 becomes very simple.
Yeah, so let's move on to the next week, which is that's all for this week, I think. Yeah, sorry, remain to the orthogonal and inner product. So let's solve this one. Maybe while solving we can.
It is option 2, sir.
Sir, in week 8, do we have to give importance for Gram-Smith process?
Yeah, maybe. Yeah, not important means Gram-Smith is, see, Gram-Smith is a process to find orthonormal basis while there is a given basis. Like what it means that suppose if you have a vector v which is also an inner product, and suppose a basis is given, e1 e2 e3 something is given. So what is the Gram-Smith? Gram-Smith tells you what will be the orthogonal basis of b. Using these bases you can find using that process. So let's solve this. Then maybe if there is an important, I will, while discussing this question, I will maybe reach there and I will tell you this is an important. That's why I emphasize here so much. Let's do that, this one. So
It is option 2.
So okay, so why this option is true?
So make the dot product between these two and make it equal to 0 because they are orthogonal.
Okay, this says these two are orthogonal.
So a plus b dot a minus b
equal
to 0. So a square minus b square equal to 0. So model.
So this gives a square b square. Why this give a square b square mod of a square? How is your say? That's the okay. It will give, but the need is
you can apply the properties.
Yeah, you need to expand it. The
yeah,
properties of inner product.
Oh.
Yeah.
Okay.
Yeah, don't go with like this directly. It will be multiplied. No, it will never.
If it is given with the usual dot product, then it is okay. But if it is not, then it becomes.
Yeah, correct. So what are the properties of an inner product? This is a function. This is said to be an inner product from vector space to R kinda, which is V. The first property is V greater or equal to 0. Or is that no? No, I think what is those? Let me see that. Okay.
Yeah, it is. First one is that positivity.
Positivity. The second one is symmetricity. And third one is linear. You can say, if you want to say in linear property. Let's say this is W. So this should happen, which will we uses here V W, and plus here plus will be and U W. And this one and next one is there is another
scalar multiplication.
Scalar
multiplication, that is
CV common U.
CV and U equal to
C into V.
These three property. If this function, this is just a notation, so don't worry. If you notate with F, that's all. So this notation means when this is a function, if it will be satisfy these three property, then this F is a inner product. So as here, so we have what we need to go when it is like this. So we have to use this linear property because this tells a relation between like this. So it means A plus B and or maybe like this A and A minus B plus B A minus B. Okay, this is equal to 0 is given as orthogonal is A plus B and A minus B are orthogonal or orthogonal. Okay, now see this will work because of you can symmet it like this, you can exchange and then expand. Otherwise, directly you can expand. It will work as like this: minus a b plus b a. Yeah, it will be b a minus b b. This is equal to 0. These all are implies. This imply the next line will be this is. So there is another concept which is
Norm of A. Yeah.
Norm of A. Norm of A is root over inner product with itself. This is norm definition. And norm is nothing but a function from V to R satisfying the properties which you can say. The first property is
Norm of X
positivity.
plus.
Yeah, positivity. The second is linearity. It will be like this, I think. And third one is what?
Scalar multiplication. C.
Scalar multiply. This is if this is happening. C mod of C. Norm of this one. If this function, you can again say this will change with F. So this is if this function satisfies these three property, then this notation, if you are saying this notation is a norm called norm. So as here this will become norm of A.
Sir, like as we discussed, that norm of the vector is dot product of the vector with itself and the square root of that, right?
So yeah, take the inner product with itself and take the root of that.
So whether all these three conditions are satisfied in this case also?
Here it will satisfy. You can check that.
Okay.
Actually, you can check that because see, this is greater than 0. See, you know that A just now we know that greater or equal to 0. And
let us finish this problem, sir. When I have a doubt, I will request you to go to video 7.4, 16 times 10, 16 minutes. Let us finish this question first, then I will request you.
Okay. So yeah. So this is this one. Okay. So this is going to be norm of A, and as again A and B are orthogonal, so that means this is going equal to 0. This is also orthonormal. This is goes to 0, and this is tells you a norm. This gives a norm. Sorry, there is one thing. Square root. Sorry, I made a. This is the norm, right? So it says implies
square equal to
this. So this will be equal to 0. So norm of A square is equal to norm of B square. Now, as you know, both are positive. Norms are positive. That means this implies norm of A equal to norm of B. Otherwise, suppose there is a negative also coming, then you have to consider negative terms also. But because of the positivity, because norms give always positive, that's why it says norm of A equal to norm of B.
So sir, why my approach is wrong, sir?
Not no approach means, see, you directly multiply it with like this.
Yeah, so I take the normal definition.
No, how you can directly multiply? Like that's the thing. Like this is the long, not long. This is the process you will do. How this this implies A plus B into A minus B. How this is? This is there is no relation like this in inner product.
We have to expand by the inner product.
Then you are able to do, right?
Yeah. So it is by fluke it is coming actually.
No, without components we cannot do it actually.
Yep, correct. By fluke it is coming. By chance it is coming.
So here the second option is correct. First option is not correct, right?
Yeah. So first option is, there is nothing said about. First option is there is a term orthonormal. If said here is term orthonormal, then this going to be correct. Otherwise, there is no orthonormal. Orthonormal means vector have norm 1. If two vectors A and B are said to be orthonormal, it means these two are orthogonal and norms of A equal to 1, norms of B equal to 1. Okay.
Yeah.
Yeah. So yeah, in chat I am looking. Somebody says not mention about dot product. So see, one thing I want to tell you. Suppose if you are suppose you are dealing with inner product and there is not mention any. If you're dealing with in R2 R3 in kind of R2 R3 and not mentioned inner product, what will be the inner product? Simply assume dot product, because in this
Normal
question
dot product. Normal dot product.
yeah normal, because there is nothing. See, you can see, you can assume other than not dot product. That should also true. That will also true for this is true for any dot product. This will true for any any inner product.
In the product. Okay.
But you can deal with the dot product. That's enough to solve. So suppose there is no not mention any inner product. Assume with dot product and solve the question. So yeah. So next is next
Sir,
is
here A plus B and A minus B are orthogonal. Then in solve, B took as AB as orthogonal and BA is orthogonal.
no, your voice become very slowly. It's can you repeat again? I didn't get what you're saying.
Sir, in solving this problem, here we took AB as a orthogonal. How it came actually?
So here it says, it already says, these two, consider two orthogonal, A and B are orthogonal.
Okay.
In information it is given. That's why I did. That's why I use.
Okay,
Otherwise,
okay. Oh, I thought A plus B and A minus B are orthogonal.
so it is also given A plus
Okay.
B and A minus B as orthogonal, but already before there is a information also given.
Okay, sir. Okay. Thank you.
Okay, so now next move on to projection. Just now we discussed orthogonal, orthonormal, and inner product and norms. There is projection. Okay, so this is a question from your solve with us, maybe solve with us, but a beautiful thing. It will discuss most of the like what is the projection. So can you solve this? It maybe it will take time, but let's do. I'm giving a small time. Let's say 5 minutes or maybe 2 minutes. Okay, I'm looking. Ganga Prasad is saying something. Okay. Yes, sure. Sure, I will. I will check. Yeah, if I will change the slide, then you will not see. Just wait some small one, maybe 1 minute. Then we can. Many of you will note this question. Then we'll do. So anyone of you got answer is 3 in chat. I am looking. Umang is saying answer will be 3. So okay, let's see that. My intention to, maybe I will not do whole question, but my intention is to know the projection and how to find, how to solve this question. So I don't know also what will be the answer. While solving, maybe we will reach to the answer. Okay, so let me know. Let me reach to the Ganga Prasad question. Maybe hope you all of you noted that question. 7.4. Timestamp is
16 minutes, sir.
16. Maybe here. Okay. So.
Sir, we just now discussed, like, inner product is the. Hello, sorry. Norm of a vector is basically the square root of inner product of vector with itself, right?
Just 1 minute. Don't we let me also add one thing for the inner product. For the inner product.
So
if suppose that space is talking about inner product also, then you want to considering norm as using the inner product, then norm of a single vector you can think as root over inner product of
vector with itself, right?
Yeah.
So what different condition is applied over there? I'm not able to understand why we are adding, mod of x1, mod of x2.
Here, see, no. The what is happening here? See, this is Rn, okay, R3, R2, whatever you are considering. Let's say we are considering R3. That is for Rn. So that is, see, R3. Suppose for this definition, whatever sir is discussing.
Even in R3 also, sir, we had discussed the same thing. That
it will, it will come. Yeah, it will come like let's say this is x. So x1.
You can take 1, 2, 3, and then.
But that's this much will come. X is x1, x2, x3. So see, this is saying, sir is saying norm on R3, not saying norm induced by inner product. So don't confuse norm. So here is mean to.
No, sir. Could you please repeat again, sir?
Norm induced by.
Take a vector, sir. 1, 2, 3. Let us take a vector 1, 2, 3.
1, 2, 3. Okay.
If I have to find the norm of this particular vector, so whatever I have understood so far, what I will do, I will take the square root of. Dot product of vector with itself, right?
So yeah, no. So please consider norm induced by inner product. This is this one. Norm induced by inner product. Norms is we are getting norm after taking inner product and root. This is just only norm, not induced by. So don't be confused. This is just a norm. This is just a norm on R3. Not saying we are now, see, suppose here we are not saying R3 as inner product. R3 is just a vector space. But when we are think when we will think R3 as an inner product with respect to dot product or maybe any inner product. So norm induced by that inner product is this one. So no need to confuse here, yeah, or this video.
So here what is happening when we are taking mod of x1, x2, x3 and we are adding them, then what is happening here?
So that is nothing but like here is, sir didn't talk about norm, sorry, inner product. He's just considering norm. This norm is not induced by inner product. First of all, you can, this norm is not induced by inner product. Here this norm is induced by inner product. We are using this here inner product.
So in the slide, does it mean that it's purely the addition of coordinates?
If you suppose somebody says find the norm is defined like this. Find the norm of this one, this vector. It's because 1, 2, 3 is a element of R3 of the vector. So what will be the norm? With the norm 6. Is he said defined. It will 6. Be norm of it will be 6. Norm of 1, 2, 3 will be 6. Now suppose somebody says, suppose R3 is an inner product with dot product, then what will be the norm? What will be the norm induced by that inner product? So you have to find inner product, then you have to calculate. Sir, here is nothing.
Sir, just correct me. Isn't our understanding that norm is nothing but length of the vector, right? And when we talk about length of something, then it is basically the distance from the origin.
Norm is not length. Length is different thing. Length is just taking the root of 1 square. So don't be confused. There are so many definitions. So but don't be confused.
Even sir has also used somewhere that in norm is length of the vector.
When sir will tell you that vector space is an inner product with respect to dot product, then length is actually the norm. See, let me write.
Length we mean the Euclidean distance.
See, length is means, see, length for this vector is this one. Okay, this is from R3. Now there are 3 different things. Suppose somebody says find the norm of this vector and norm is defined like this. So you will directly use this definition and find the norm. Somebody says suppose R3 is an inner product with respect to dot product, then find the length of this vector ABC. Then what it meant that you need to find the norm, and norm is nothing but the inner product of with itself. So length or norm of, not length, sorry, norm of this vector. Sorry, here is, let's say this is V. Norm of this vector is this one. Now somebody says there is no concept of vector space inner product. Somebody says find the length of an element ABC. See, I am saying different word. Find the length of an element which is this one. So what is the definition now? A square plus B square plus C square. That's it.
ABC is also a vector, no, sir? ABC
so no. So I am saying R3 is a set. No, not say. For this case, we are not considering R3 is a vector space. For this, just consider R3 is like a coordinate, and here is work as a Euclidean. But here is we are considering R3 as an inner product, and here we are considering R3 as a norm linear norm space kind of. 3 definition.
I have a doubt over here.
Just to conclude, sir, whether length and norm are same or different things?
Norm is different and length is different. Okay.
So, why they are used interchangeably?
Why we are interchanging? The reason is, see, when somebody is asked norm and given that he defined the norm like this or maybe differently also, and asking for norm, then you will find norm. But somebody is directly says find the length of a vector in R3, then he didn't tell you about any norm. He didn't tell nothing. Nothing said about the norm. So directly use this definition. Okay. So there are 3 different things. This is regarding somebody is given norm and then asking for norm. then you will apply. Somebody says R3 is an inner product, then find the norm, then you will apply this one. If somebody says R3, there is an element in R3, find the length of that, then this is just taking this one. Okay, these three are.
So the length that you are writing, that a square plus b square plus c square root over, that is from, like the length from the origin to that.
From origin, yeah, length from origin. That is the length means saying to be, the word is length means taking the distance. This is like in you are in coordinate system. In separately, if you, separately I am saying this is like a coordinate system, but here is an inner product space, and here is the vector space. These three are difference, you know. This is a vector space, and then norm word came here. This an inner product space, then norm word came here with defined like this, and this is like a coordinate system, and then length word came here. Okay. So don't confuse. Okay, okay, Ganga Prasad.
Okay.
Yeah. Okay, so okay, so let's solve this. So
what is the answer? 4.
Somebody says 3. I don't know what is that. This is from your actually. Let's see. Maybe someone is saying to be 0. Maybe probably 0. I think so.
Yeah, 0. Yeah.
Yeah, it will come 0. Not 3, not 4 also, not 6 also. It will 0. Let's see that. So what is projection? See, projection is in like when you in coordinate system, when you are in coordinate system, I am emphasizing on coordinate system. So when you are in coordinate system in R2, suppose there is a element. I'm now saying element, not vector. I'm saying element. This is AB. So this is B. This is an element of R2 AB. You want to find the shortest distance with this line. So actually projection is one kind of give the shortest distance between two vectors or a vector and a space on and subspace. So those are like, if you see in videos, I have clearly told about that. Otherwise, you can just remember the formula also, that's enough. The projection of a vector on a subspace, or projection of a vector on a vector, or projection of a vector on itself on the means vector space. The terms I am writing. Projection of a vector, let's say A, on a vector B. Projection of a vector A to on in it will be maybe 2 here, to a subspace, let's say W. W means surely it is given that talking about, see, vector word came, that means there will be a vector space, and vector and subspace word came, that means there will be a vector space, and W will be a subspace of that V, and it will be a vector of V. So there are two things: projection of a vector on a vector, or projection of a vector on a subspace, but both have the same formula. What is the formula? Projection says projection in notation form, projection P to a vector B of A equal to A, B, and B here. But the condition is B should be unit vector. To change it to in unit vector. What means? It means writing to be like this: A, B, norm of B. This one. Now next is projection on a subspace of a vector A equal to, okay. So this is need to be remember. So here is definition defined on the basis of that subspace. Let's say V1 is a basis, V2 is basis. Okay. See, these
the
all
first
are
one is the projection of A on B, right? The first one.
projection of A on B. Yeah. And this suppose basis of B1. See, these are not a vector space, actually inner product spaces. Inner product. So that's why we are able to use inner product. So actually these are inner product. So let's say V1, V2 and V3 are orthonormal basis of this W, or maybe if you are assuming 2 only, let's say this is a vector and let's say this is R3. The whole inner product is R3, subspace is W, which having basis orthonormal basis B1 and B2. So the definition says A V1 V1 plus A V2 V2. These are orthonormal, not orthogonal. Suppose you got orthogonal, so you have to change it with the norm. That means you have to, what you need to do, take the norm, divide with the norm of B1 plus A V2, divide with the norm, plus V2 divide with the norm. This gives the projection of A on W. I hope.
Sir, V1 and V2 are orthogonal basis of W.
If the case is orthogonal, then you have to divide with the norm. If the case is these two are orthonormal, then means it have norm 1, so no need to divide, or it will be become 1 itself. So that is the simply you will get this one.
So V1, V2 are in W, right? V1, V2 are in W, right? W in the product space. V1, V2 are in W, right?
This V1, V2 is the basis, orthonormal or orthogonal basis of W. Now let's do our question here. We want to find the what is that? If ABC is the projection of the vector 1, 0, 1. So means ABC is after projecting ABC. We got this one after calculating this whole thing. ABC is that, and A is your projection, projecting VR, when A is your 1, 0, 1 on subspace, which is subspace is given like this. These are the subspace, vector space, not only vector space. You need to be, see, whenever inner product is not mentioned, always assume inner product as a dot product. Okay, as here is not mentioned, here just said vector space. So inner product is actually for R3 is dot. Just assume there is no error, there is nothing, maybe many times.
Anyway, they usually inner product, so it's not.
If somebody is intentionally ask some different, then surely he will mention the inner product, otherwise not. Okay, yeah. So so this is so subspace is your this one. So we want to find the projection, that is ABC, asking that is numeric is that. So how to find now? So we have to find orthonormal basis of this subspace. So what is the process to find? First find a basis of this subspace. So let's find that this is x minus y plus z relation is given. So you can write x is equal to y minus z. So I want to find a basis, assume y is equal to 1 and z is equal to 0. So this means x is equal to 1, 0 will be a vector, and another one y is equal to 0 and z is equal to 1. So it will be minus 1, 0 and I think 1. So you got 2. So that means you got a basis of W, if you are assuming this is W. So basis of W, basis not equal to, it will be basis of W. Now see, whenever you have a vector collection of vector, if you want to change it in orthogonal, because Graham-Smith process gives the orthonormal basis. Graham-Smith process gives you orthonormal basis. So you have this one, you want to find orthonormal basis, so use Graham-Smith process. What is the Graham-Smith process? Suppose this is U1 and this is U2. So Graham-Smith process says, let's say you got using the Graham-Smith process B1 and B2. So V1 equal to U1, u1 upon divided by u1. And next, what will be the v2? V2 will be u2 minus inner product. If you just remember, I am not going to recall it, that is a process only, that's all. So the process is like this: b2 minus u2 minus u2 v1, and this is v1. So that means you got here 110 divided by norm, it will be root 2. So v1 is equal to this one. v2 is still remain, so let's find v2. v2 is u2. u2 is minus 1 0 minus 101, and v1 is your 110 upon root 2 with 110 upon root 2. So this final thing will give maybe minus 101. Here is next after the, it will be minus. Take the inner product, it will be, you can see, you can make it out here. So it will be 1 by 2 or maybe
minus 1 by root 2.
Minus 1 upon not root 2, it will be 1 by 2, become 1 by 2, right? It will be multiplied with this also.
Yeah,
so
yeah,
it will be 1 by 2, and take now
it will be plus, na? Plus.
Let's see that. Let's say I am solving. Let me solve this. This will be 1 by 2, and this will be minus okay, minus 0 0. Oh, so that's why you are saying to be plus here. And so, and this will become 1. So final thing will be 110, I think, this one.
Yeah.
And so it will be so v2 is actually after, v2 will be after dividing with the norm. This will remain to be. See, this will give this one. Now v2 will be after dividing with the norm. So let's find first that one. So it will be minus, this will be 1 by 2.
Minus 1 by 2.
1 by, sorry, 1 by, minus 1 by 2, 1 by 2, and 1. So now v2 will be, see, whatever, that's why just please be consider with the, that sir have, that's why word used w1 also w2. The reason is the thing are like v1 equal to u1, and w1 will be v1 divided by norm. v2 is equal to this one as this one, and w2 will be just divide with the norm, v2 upon norm. So w and w2 is the orthonormal basis. So we got this one. We still we remain to ortho, make it orthonormal kind of. So divide with the norm. So whatever norm, let's say divided by this. So whatever something will norm will come.
3 by 2.
So 3 by 2. So 3 by 2. Okay. Root over 3 by 2.
No, root over 9 by 4. So 3 by 2.
Okay, 3 by 2 with this. Then it will become 2 by 3 and minus 1 by 2, 1 by 2 and 1 something.
Yeah.
So first one you got 110 upon root 2, and second one is this one. So let's say this is W1 and this is W2. Now use this formula. Now what it means that you need to find the dot product with the projection will be of 101 on W will be, take that 101 with this W1 and outside W1 plus inner product with 101 with W2, here is comma, and outside W2. So if you solve this, you will get the answer. That's all. I am leaving to you the calculation part. Okay. So that's the.
Just have a doubt, sir. The basis that you are taken, product, sir. So for the subspace, we have taken the basis from equation given x minus y plus z equal to 0. So just equating, assigning one x as 1 and then solving for y and z, right? So, but in this case, we would get two bases. But how do we know we have to stop with two bases? Why not three as a basis?
Yeah, actually, the reason is see, you know that this is we have like a system of linear equation with a single system, right? With a single equation. So in such cases, if you want to find the solution, so x can be written as like this. So what will be the solution? If you want to, somebody's ask, what will be the particular, see, this system has infinitely many solution with, or you can say there are two independent variable this system has, right? That's why it's having only needed to 1 0 and 0 1, because you want to find a vector. See, one time, see separately, see you know that how to find a basis of when it is given like this. See, that is the process. Like you are able to give, here are two independent variable, you can see that y and z. So once give 0 and another give 1, so it will give a vector, because two independent variables. So independently I am giving, you can give 1 1 also, no matter, give 1 1 but differently. Like this will be, now see, this is 1, this is 1. Okay, now suppose this is again you are giving 1 but give 2, because so that you will get a independent vector. The intention is I want to find two independent vector. That's all. That's why I am choosing 1 and 0 or 0 1 or 1 2 independently we have to give, so that we can get an independent vector. No?
Yes, sir. Got it. My question is, how do we decide that, okay, let me stop at getting two as a basis vector rather than getting three, right? Like in the sense, because subspace, it might also be in R3, right?
So region is using this one, you can say, see, whenever is like this, then you have system of linear equation only one. Only one's equation. So that means this system has two independent variables. So that means this can
dependent variable. So
one is dependent, two is independent. So independently just give value. You are able to get two independent vector using that. That will be expandable. Expandable.
That is expandable. So that you can stop at that. Okay. Thank you.
So let's move on to the next question. We discussed for projection, orthonormal, orthogonal, premise with. Next is remain to the orthonormal transformation, orthogonal transformation. That is a very useful thing also. That is, so most of the time you have seen that we asking from orthogonal transformation, orthogonal matrices are very much useful to, because once you have a orthogonal linear transformation, you can get a matrix representation of that, and that will work as a orthogonal linear transformation. So discussing about the linear transformation, it's enough to discuss about the matrix. That's I mean to say, discussing about linear transformation, discuss about the matrix, and then you know that how to change. It means a matrix representation of a linear transformation, and both are exactly very, means there is a, you can say, a relation. If you have a linear transformation, you will get a matrix. If you have a matrix, you will get a linear transformation. That's why discussing about linear transformation is enough to discuss about matrix. So this question is, let A be a orthogonal matrix of order 5. Then which of the following option is going to be true? The rank of matrix is 4, A, nullity 0, a transpose with orthogonal matrix.
2, 3, 4.
Okay, 2, 3, 4. I will, okay. Okay, I will ask from you that how is, let's others do, or let others, what will be the option will correct, which option will correct?
So 2, 3, 4.
2, 3, 4. Yeah.
2, 3, 4.
So
what is an
how many?
orthogonal matrix, first of all?
So the one thing is, orthogonal matrix is, suppose you have a matrix A and just take the transpose of A, and suppose this is happening. Identity. Then A is called orthogonal matrix. That's all. And that's enough to deal with rank, nullity, all things. This only this property you can using this property. What let's do, and let's see that how it's happening. See, you have this relation. Just take the determinant of this. It means determinant of identity. What will happen means it will separately work like this, and determinant of identity is 1. Now you know that determinant of A and of a matrix and transpose, determinant transpose are the same, means have same determinant. So that means determinant of A will it will become also determinant of, which is 1. Determinant of A square is equal to 1. Sorry. So determinant of maybe plus or minus 1. Okay. So determinant of A may be plus 1 or minus 1. So what it says? It says determinant of A not equal to 0. What it mean? Rank of A surely of the order, whatever order. Means surely it will not below of that order. Exactly, if it is 5, then it will be 5. If suppose order of matrix is 4, then it will be 4. So rank of that matrix is exactly the order of matrix. Another thing is, use the rank nullity theorem for matrix. Using that you can decide nullity of that matrix. So rank nullity says rank plus nullity equal to order of matrix. So nullity, rank is 5 and nullity is we want to find is equal to 5. So nullity in such case is 0. So see, only you know this one, and that's enough to decide all.
But here order is 5 and rank is 4. How do we do this?
So suppose, see, 4 means your matrix is of order 4 plus 4, right? You see, orthogonal will be always a square matrix. So don't worry with that. Always a square matrix of fixed order with finite order.
And all the vectors will be independent.
All the, that's another conclusion is, from here you will decide how it's happening, the independent. Say rank is 5, it means what it means is all the columns, all the rows are linearly independent. Why? Because rank, if rank is 4, then such case will happen, means 2 rows will be dependent, then rank will be 4. But here is rank is 5, that means all rows or column are independent. Another thing you can conclude, what you can, the rows are linearly orthogonal, not orthogonal, orthonormal to each other. If you check that, rows will be orthonormal, not orthogonal only. If you check, rows will be, or columns will be orthonormal to each other. Then it will be. If you check, why? Because if you multiply with A and A transpose, row become column here. So that means applying, you are multiplying row with the another row, and that gives 0 or identity. That's why you can decide that rows or columns are orthonormal to each other for that matrix. And another thing is, as determinant is non-zero, then see, not 0 means say is invertible. So using this one, you have concluded many things about the rows and column, about the rank, about the nullity, about the invertibility. So that's the, if somebody is asked some there is some different question, but try to conclude using this one, because you have only this one, this option. This says only the orthogonal of matrix. So try to conclude what possibilities is going to happen using this property. So from here you can conclude these are maybe true or false.
The rank here is matrix is actually 5, right?
So rank is is 5 as here, but here, so that's why it is not true. Invertibility, as you got written, determinant is plus or minus 1, so that means non-zero, so it will be invertible. Nullity, as just now we calculated using rank nullity theorem of matrix, we got 0. A transpose is orthogonal. So yeah, what it mean that we have A, and we know that A is orthogonal. So what about A transpose? So let's find A transpose into A transpose of transpose. That means identity, right? So A transpose, it will be A itself. And actually A is orthonormal. So you can say A transpose is also orthonormal.
Orthonormal.
Oh, sorry, orthogonal.
So this one I didn't get that. A transpose into A inverse. What is it? Just
No, not inverse. This is transpose. Sorry. So I
Okay,
want
no,
to
no.
check A transpose is also onward or not. So that means what is the definition says? A transpose, we have A transpose of transport. This should be identity. And this is equal to A transpose A itself. And we have already given this one. So that means this is identity. That means A transpose is orthogonal matrix. It's also orthogonal matrix. Right? Okay, so that's all for today from my side.
I have a small doubt.
Okay, so what is that?
Sir,
For me, your voice is breaking, or for all of you?
For everyone.
sir,
All of
because
us.
A is a orthogonal matrix, then product of two row or two columns should be a 0, isn't it?
Product of two row, so
rows
maybe 0 or maybe 1. So reason you can see that if you multiply A and A transpose, so whatever, like here the first.
Yes, sir. Now am I audible?
Yeah, you are.
Hello.
Yeah, hello, am I audible?
Yes, sir, you're audible, sir.
So actually he asked about the so actually any two row in that matrix, any two row will be orthonormal to each other.
Sir, so the matrix when multiplied with itself will be 0, right?
No, not a multiply. Yes. How it will be 0? Multiply with itself.
No, sir, because any of two row product of any two rows should be is equal to 0. Then A transpose is equal to convert to row into column. Then if we are trying to multiply row with another row, then it should be also 0.
But you will multiply with the you will multiply with itself, right? Also,
yes,
once you will multiply with itself also. So that will give you 1. That will be give 1, and rest all will give 0.
Yes. Okay. Got it.
Okay. Yeah. So that's for from my side today. And sorry.
So I have a doubt.
No, for me it's breaking, or I don't know.
It's breaking for me also.
Okay.
Hello, sir. Am I audible?
No, your voice is breaking.
Hello.
Yeah, it's now clear.
Hello. So in this projection question, so finding the basis for subspaces, right? And now we need to make them the orthonormal.
This projection.
Did you use the Graham-Smith process to find the vectors for the subspaces?
I used Graham-Smith process. After getting a basis, I used Graham-Smith to find the orthonormal basis.
But sir, we also can find the orthonormal basis by dividing them by the norm.
Yes, there is a way. Directly you can.
Okay, sir. So we can divide it by norm, we'll get the orthonormal, right? So
you can get a basis. I use Graham-Smith. It can have a basis which is also orthonormal. So but you have to check which one is going to be. Unable to decide exactly you are at exact orthonormal basis, it's difficult to find. But after getting any basis, you can make it orthonormal, and then you can do, because you have Gram-Smith process.
So 1 upon root 2 into 1 comma 1 comma 0 and 1 upon root 2 into 1 comma minus 1 comma 0. These are orthonormal, right?
That's the thing. If you are able to directly find, that's the very good thing. You can quickly find, and you did that.
So then can I use these vectors as well for finding the
because see, projection says
but
any
but
orthonormal.
But the two vectors are not orthogonal, right?
Say, okay, that's your part.
Sir,
you need
when
to check.
we find the basis of a given subspace, if the basis is orthogonal, then we can directly divide by norm.
Yes.
Else we have to do the
If you
use the Gram-Smith process.
if you found the orthonormal, just use the projection formula. Others you are unable to find, then find a basis and make it orthonormal. And all the if you find any basis, any orthonormal basis, if you use projection formula, it will give a unique vector, because the projection gives a unique vector because of uniqueness. Sir, have told you about.
There are much chances that our orthonormal basis might be different, sir, but answer will be same.
Answer will be same. It will not differ because of it.
Okay, sir. Okay, thank you.
Okay. So can we close session?
Yes, sir.
Yes, sir. Thank you, sir. Thank you.
Actually, I have an earlier doubt, sir. From week 6, just one activity question.
Matrix representation.
A activity question in 6, sir. Week 6.
Okay, yeah, you in a starting you said okay, activity, which activity? Week 6?
6.2.
6.2.
I mean, I think I forgot certain concepts actually.
Which question number?
6.2, 8 and 9.
8 and 9.
Yeah,
Okay.
these two, sir. So actually, yes, sir. For calculating the
okay, T such that T. Yes, okay, which of the following linear transformation isomorphism between this and these two?
So just trying it out, but I'm getting the just equating it to 0 vector, but I'm still not getting it. So, confused.
So see, the best way is what I tell you. If you asking for this is isomorphism or not, so see, you can find a basis of V, you can find a basis of W, and find the linear transformation for matrix representation of each, like for this one, and find the rank of that. If rank is going to be exactly as because these two are, you can see that both are the R2 to R2, because V have dimension 2, W have dimension 2. Okay, so find the matrix of that and find the rank of that. If rank is 2, then you can say, oh, because that is the invertibility of that matrix is invertible in such case. So that means T will be means what? Rank of T is 2. What it mean that nullity is 0? That what it mean that T is in isomorphism or not? Like that you can do. And also see here is deciding quickly is difficult. Just find a basis of V and find a basis of W, find the matrix representation of T, and find the rank. And from rank you can decide which one is going to be injective or not, or surjective or not.
So can I say one thing in this question?
Otherwise, if you have another trick, then that will be more better.
We can say this is a trick. So in the first option, we don't have the value for Z. So it can't be isomorphism, sir.
Oh.
So in second vector, we have X and Y as same. So this is many one type. So this cannot be isomorphism as well. If I'm not wrong.
Oh, okay. So Z is not here.
No, yeah. So Z is not present in the first option. We don't know what could be Z. In the second, we have X and Y both as a Y. So it means we can have two values of X.
Actually,
Y,
actually the reason is as Z is not in the first option Z is not included. So that means 1, 1, 2 and 1, 1, 3 have same image.
Yes, sir,
Whatever
yes.
from here. So that means this is not going to be injective.
Yes,
Similarly, yeah, it is going to be here also. But the third
Many
one
more
is
times.
okay, yeah, that is a
Third one is it.
that is a good good thing. Yeah, that is a
But
very good.
if you just click on check answers, I think it's giving it's giving this.
Let's see that.
Click on check answers. It is giving the.
Okay, is this
Then
one?
next, yes, sir. So it's giving
this
the
one.
second one.
Oh.
Second one.
Yes, sir.
Sir, both V and W are dimension of 2. Right?
Okay. Hey, because of this one here is X is equal to Y.
Equal
So
to
it
yeah.
will, oh yeah, here because that's why it's happening. You can neglect the first option, but here is the
second one is dimension 2. Third one becomes dimension 3.
3. Okay. Second one is dimension 2. So it is same as the
vector spaces.
So you can say that this is given in the question, so we can directly put X to be Y and then get the same thing that we need, right? I mean, one condition is given in the question, so we can use the condition that is given in the question and then can find the value for this question.
I got
yeah,
the
that's
one
the yeah, that's why I will say that's why find the rank of matrix, that linear transformation, that will clearly tell you. And rank of linear transformation is you need to find the matrix representation of that and find the rank of that. That's the correct ways.
So which means we have to, like you said, take a basis like
easily see, it will not take time. Easily you can get, like substituting here 1 and 0, same here is as previous 1 0 0 1, you will get a basis. Again here here is you gave 1, again 1 0 and 0 1, it will, again you will get a basis for W. Just quickly take the image and expand of that and find the matrix T for T1 for T2 and find the rank.
Yes, so you can, I mean, for just this one 8, can you quickly take that example? So 9th one, I'll do it myself, like 9th and 10th alone. For the 8th one alone, can we just do that? 9th one is similar one.
Okay, so
for the 8th one, if you can just take that example.
8th one.
Yes.
Isomorphism is in this question.
Same. Yes, sir. I mean, like I'm talking about the calculation part. If you can take the basis part and complete that, so that I can.
Okay, so for V1, so let's find V1. The basis will be X is equal to Y minus Z is given. So take Y is equal to 1, X will be 1, Y is equal to 1, and Z is equal to 0. One basis will be this one, and then another one element will be this one. Another element will be -1. And 0 and 1, give Y is Z is equal to 1 and Y is equal to 0. So this is a basis. Now for second one, W, the basis will be, your equation is
X equal to Y.
X is equal to Y. So give Y is equal to 1, 1, 1, and Z is equal to 0. And second one,
0,
Y is
0,
equal to 0, 0, 1. So this will be a basis. Now T of 1 1 0 will be, quickly you can tell, this is 1 1 0. 1 1 0. One element find. Okay, and -1 0 1, it will be
-1
0 0 0, right? Because Y is here and Y is 0. So see, from here itself you can tell. See, you have a non-zero vector which have image 0. So this will never be a injective, because injective means 0 is 0 to 0.
No. This is sir. It will be.
Yeah, this will be 0 0 0 because T of X Y Z is equal to Y 0 and Y is 1.
It is not 0, right? It is Z. So it will be 1. 0 0 1.
No 0 0 no 0. Last one is 0. Not Z is here. Last one is 0.
No, which?
No, sir, it's a Z, no?
1.
No. Oh, your second. I am saying for first one.
Okay.
Now for
First one
second
is
one,
eliminated, yes, second one.
for second one, image will be 1 here. So that means, and you can see that. So best way is, so here itself you can decide. You can see that this one is independent to this one. What it mean that? This is a basis. This is a basis of. This is means this is a element of this one. Means these are two are image of element of basis. Now see that this is a vector of that W. This is a vector of W, and you can see that both are independent to each other. What it means it? It means that for independent, you are getting independent two vector independently. This says that the rank of T itself will be 2. So there is actually a theory. Otherwise, you just write the matrix. You will get the it will be 1 0 and second one will be 0 1. So directly you can tell. See this have rank 2. So that's why rank of T will be 2. So T is injective. Sorry, injective, surjective isomorphism. Otherwise, there is also a relation. If you say suppose V1 mute
please mute all.
Yeah, let me mute to all. Yeah, thank you. So there is a relation, we can say. See, we have a linear transformation from V to W, and suppose V1, V2, V3 collection of linearly independent from V, and W1, W2, WK linearly independent. Let's say both have n also. Dimension is n. So let's say Wn is independent vector, and mapping is like this: V1 maps to W1, V2 maps to W2, Vn maps to Wn. So what it means is linearly independent map linearly independent vector, or maybe it will be W2, it will be W1. Nominator meant to say image of linearly independent vectors are linearly independent. In such cases, what it means is T is injective. T is injective because injectivity it's happening. You will later when you spend some time on this, you will get because of this property. You can directly tell, otherwise write the matrix and decide that. This is a beautiful property of linear transformation.
This one didn't cross my mind when I was trying. That's why I got.
No issue. So okay, that's 7 now. So can I end the session?
Yes, sir. Just for 1 minute. So this for these questions, the basis computing the basis or arranging at the basis is the best way. Because is there any other way? Because the arranging at the basis.
See, many times always not tricks or not easy way. See, sometimes there are lengthy process, but those lengthy process can be very quickly done using when you are very much, you have more, you did many, you have done more practice. So it's like for me, I very quickly I found the basis, and very quickly I found this matrix representation and decide that okay, this will never be. So sometimes practice is because for each question you are not always find a trick. That's I meant to say.
Yes, sir. Thank you.
Let me stop sharing first.
Hello.
Yeah.
Sir, I was saying I have a doubt, sir. A small doubt, sir.
What is that?
So in the mock test paper, we have a question number 7. In that question, we have a piecewise function xy divided by x square plus y square.
No, this is maths too. Piecewise function. Where is that piecewise for maths too?
Yes, sir.
Question number 7. Oh, sorry. Piecewise function. Oh.
Yes, sir. Yes,
sorry.
Sir.
Okay.
So in that question, we have option number first, which is saying all partial derivatives are exist. So I'm not getting why it is saying this. I mean, what is the meaning of this all partial derivative exists? I mean, do we need to find the derivative along x-axis, then y-axis? Then we can say that yes, all the partial derivatives are exist.
Actually, there are two variables, so only all means saying to be two partial derivative will say. That's all. There are two variables, so two partial derivative will exist.
No. The question is all partial derivatives exist, so I need to find
all
the
partial derivative of order 1, first order only, not all. First order partial derivative.
Yeah, first order partial derivative. I think I have to check the question again.
Yeah, actually that is.
Can you
fx?
open this question?
Okay, let me say that. Okay, so actually,
yes,
that is for first order only, and there are two variables, so only
all
two partial derivative. All the first order, not any order. All the first order. What is mean that only fx, f suffix x and f suffix y. Asking for existence of f suffix x, f suffix y. That's all.
Okay, first I think we have to use the first order principle, and then we need to say that yes, all the derivatives.
Only first order, no need to be f suffix x kind of more time. No, only first order. That's all.
Okay, so okay, got it, sir. Yes. Sir. Okay, thank you, sir.
So let's end the session. It's 9:10. Sorry, 7:10. Hope many of you got like whatever we discussed.
Yes, sir. Thank you, sir. Thank you for this amazing.
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you so much for joining.
Thank you, sir. Thank you, sir.